Hello there, and welcome to Science for Sleep, where curiosity drifts as softly as starlight and science takes its time finding the calm between questions. Tonight, we're not talking about time, but about something that quietly shapes our nights just as much. Something that's been watching us from above for longer than our species has had a name for itself. The moon, yes, but not just ours. Tonight, we're setting out on a gentle orbit around the solar system to see how many moons there really are. Sounds like a simple question, doesn't it? You'd think we'd have an exact number by now, something neat and tidy like planets or constellations, but the truth is, the universe doesn't do tidy, especially when it comes to moons. Before we start counting though, I'd like to know something small and personal. Where are you listening from tonight? Are you near a window where the sky's clear enough to see our own moon? Or are you tucked away somewhere cozy, with the curtains drawn and just the faintest glow sneaking in? Wherever you are, take a slow breath. Let the day loosen its grip. The stars, the planets, the moons, they're all still out there, quietly circling, and we have all the time we need to wander among them in thought. If you find this little journey soothing, or even just a pleasant background for drifting toward rest, I'd be grateful if you gave the video a like and subscribed. It helps this small corner of calm find others who might need it too. Now, make yourself comfortable, and let's begin, because the story of the moons in our solar system isn't just about rocks in orbit. It's about company. Every planet, every world seems to want someone to dance with. If you look up tonight and see our moon hanging there, you might feel like it's the only one. For most of human history we thought it was. One bright companion circling Earth, setting tides in motion and marking the passing of nights. But as soon as telescopes gave us better eyes, we realised Earth's solitude was an exception, not the rule. Other planets had moons too, some big enough to be planets themselves, others no more than captured boulders wandering by. And the number kept changing. For a long time, textbooks would tell you there were 173 moons in the solar system, then 121, then 214. Now, depending on who's counting and what qualifies as a moon, the number hovers somewhere beyond 290 and still rising. Every time our instruments sharpen, every time a spacecraft swings past Jupiter or Saturn, we find more. Tiny specks, barely wide enough to hold a mountain, circling their planets like quiet echoes. It turns out the solar system is full of them, a family of wanderers, all moving to the same gravitational rhythm. To understand what a moon really is, you have to start with the idea of orbit. Every moon is a balance act between falling and flying. Gravity pulls it toward its planet, but its forward motion keeps it from crashing in. The result is a continuous curve, a fall that never lands. Our own moon is locked in that dance with Earth, the same side always facing us because of tidal locking, its rotation perfectly matched to its orbit. If you've ever felt drawn to the moon, in the literal sense you are. Its gravity pulls at the oceans, raising tides, pulling them across the globe twice a day. And yet, it's also drifting away from us, a few centimetres each year. In a few billion years, it will look smaller in the sky, and solar eclipses will no longer perfectly fit. The Earth and Moon are bound, but not forever. Even companionship in space has a half-life. The question of how many moons there are seems simple, until you realise definitions matter. What counts as a moon? Must it be spherical? Must it orbit in a stable pattern? What about captured asteroids that loop around a planet in erratic, temporary paths? For scientists, a moon, or natural satellite, is any object that orbits a planet or dwarf planet rather than the Sun. That's the baseline, but even that can get blurry. Some moons are so large they dominate their systems. Ganymede, for example, is bigger than Mercury. Titan, Saturn's largest moon, has a thicker atmosphere than Mars. Others are so small they look like debris caught in a gravitational field. Some might not last long enough to be considered permanent members of their planetary family. The universe doesn't like neat borders, and the word moon has had to stretch to keep up. Our own moon was once a mystery in itself. Ancient civilizations treated it as divine. a light that waxed and waned with the rhythm of life. Only in the modern era did we learn it's probably the result of a collision. Billions of years ago, a Mars-sized body slammed into Earth, flinging molten debris into orbit. That debris eventually gathered into the sphere we now see glowing at night. The Moon's birth was violent, but its life since then has been serene. Its craters hold the scars of ancient impacts, each one a frozen memory of cosmic collisions. Its dark plains, the Maria, are ancient lava flows that cooled billions of years ago. And its surface dust, the regolith, is so fine it clings to everything, even to the suits of astronauts who walked there and found it smelled faintly of burnt gunpowder. Strange to think that something so peaceful from afar carries such a chaotic history. But then again, every moon does. When we look beyond Earth, we find that moons come in families. Mars, for instance, has two, Phobos and Deimos. They're small, irregular, probably captured asteroids. Phobos orbits so close that it rises and sets twice a day, racing around Mars faster than the planet rotates. Deimos, slower and farther out, looks like a bright dot. Over time, Phobos is spiralling inward, inching closer every century. One day, it will crash into Mars or be torn apart by gravity, forming a ring of dust. Mars, it seems, is destined to trade its two small moons for one faint halo. Even here, the story of moons isn't static. It's evolving, always moving, always shifting. Then there's Jupiter, the monarch of the solar system, surrounded by an entire swarm of moons. Over 90 that we've confirmed so far and counting. When Galileo first turned his telescope toward Jupiter in 1610, he saw 4 bright points moving alongside it: Io, Europa, Ganymede, and Callisto. He called them the Medicean stars, but we now call them the Galilean moons. For the first time, humanity saw another planet with its own companions. It was proof that not everything orbited Earth, and that realization quietly rearranged the way we saw ourselves in the cosmos. Those 4 moons are still among the most fascinating worlds we know. Io is volcanic, with sulfur plumes rising hundreds of kilometers high. Europa hides a global ocean beneath its icy crust, possibly home to life. Ganymede, the largest moon in the solar system, has its own magnetic field. Callisto, scarred and ancient, looks unchanged for billions of years. Each one could be a world of its own story. And Jupiter doesn't stop there. Dozens more moons orbit farther out, irregular, captured. Fragments of collisions or remnants of the early solar system. Together they make Jupiter not just a planet, but a miniature solar system within a solar system. Saturn's story is even more intricate. Everyone knows its rings, but within and around those rings are more than 140 moons, depending on where you draw the line. Titan is the standout, a thick, hazy world with methane lakes and a nitrogen-rich atmosphere. It rains there, but not water. Instead, droplets of liquid methane fall gently onto hydrocarbon dunes. It's a landscape both alien and strangely familiar. Then there's Enceladus, small, bright, and covered in ice. From cracks near its south pole, plumes of water vapour burst into space, feeding Saturn's E-ring. Inside those plumes are organic molecules, hinting at a hidden ocean beneath the crust. We've even flown spacecraft through them, sampling their composition. Saturn's other moons are smaller, but no less intriguing. Some shepherd the edges of rings, maintaining their shape. Others share orbits like Dione and Helene, locked in delicate gravitational balances. There are moons within moons' influence, a gravitational symphony of icy bodies and shadows. Counting them all feels less like arithmetic and more like poetry written in orbital mechanics. Farther out, Uranus drifts on its side, its poles where its equator should be. Around it move at least 27 known moons, many named after Shakespearean characters: Titania, Oberon, Ariel, Miranda. They're icy and dark, some scarred by canyons deeper than the Grand Canyon. Miranda in particular looks almost stitched together, a patchwork of ancient terrains, as if it's been shattered and reassembled by gravity more than once. When Voyager 2 passed Uranus in 1986, it captured just a brief glimpse, a few photos that hinted at more mysteries than they answered. Even now, those moons remain mostly unexplored. For the most part, they exist in silence, circling their sideways planet in a realm where sunlight is little more than a pale suggestion. Beyond Uranus lies Neptune, and with it, one of the strangest moons in the solar system, Triton. Unlike most moons, Triton orbits backward, opposite Neptune's rotation. That means it wasn't born there. It was captured, probably a former Kuiper Belt object that strayed too close. Because of that capture, it orbits in a slow spiral, gradually falling toward Neptune. In hundreds of millions of years it may break apart, forming rings of its own. For now, Triton remains a frozen enigma. Its surface shows signs of nitrogen geysers, black streaks marking where icy gas bursts from below. Its temperature is so low that even nitrogen behaves like rock. Yet, in its thin air and distant sunlight, it holds a quiet kind of beauty, a world that shouldn't exist where it does, but does anyway. Even at the edge of our planetary family, moons continue to appear. Pluto, though reclassified as a dwarf planet, has 5 known moons. The largest, Charon, is so big relative to Pluto that they actually orbit a point between them, a double world locked in eternal balance. The others, Nix, Hydra, Kerberos and Styx, are tiny, irregular, probably fragments from a collision long ago. Their orbits are chaotic, constantly tugged by Pluto and Charon's gravity, yet they persist, circling their frozen parent world in the farthest reaches of sunlight. And beyond Pluto, we've found dwarf planets like Eris, Haumea and Makemake, each with at least one known moon. Even in the deep cold where the sun is just a bright star, companionship seems to endure. It's as if the universe dislikes solitude, even in its most distant corners. As telescopes grow stronger and spacecraft venture farther, the number of known moons continues to rise. Some are discovered by chance, faint dots moving against the background of stars, noticed only when astronomers compare images taken days apart. Others are found by missions like Juno or Cassini, orbiters that watch closely for subtle gravitational effects. Many of these tiny moons are less than a few kilometers wide. Some might even be temporary, captured for a while, and then flung back into independent orbits around the Sun. Counting them becomes an exercise in patience and humility. The number isn't fixed, it never will be. The solar system is alive, not in the biological sense, but in motion, forever rearranging itself in slow, gravitational choreography. It's interesting, though, how we always come back to our own moon as a reference point. It's familiar, predictable. It defines our sense of what a moon should be. But when you look at the diversity out there, volcanic moons, icy moons, rocky shards, hidden oceans, our single companion feels like just one example of a much wider category. Earth, in this respect, is modest. Not the most moon-rich planet, not the most extreme, but perhaps the most relatable. When early humans looked up and saw that glowing sphere, they didn't know they were looking at a rarity. To them, the moon was the sky's heart, the rhythm of night, and in a way, it still is. When you think about the moon, you might imagine it as a silent partner, a glowing witness to every night we've ever lived through. Long before anyone knew what a planet was, long before words like orbit or gravity existed, people looked up and saw it as a companion. It wasn't an object back then, not really. It was a presence. It rose and fell, changed shape and disappeared, only to return again. For early humans, that rhythm must have been one of the first dependable things in a confusing world. The moon's return was a promise, a quiet assurance that the sky still cared enough to keep its appointments. The first people to track the moon probably didn't call it that. They just noticed how it waxed and waned in cycles that matched the length of a month, how it influenced the tides, how it glowed without fire. They learned to mark time by it, planting and harvesting, travelling and resting. You can almost picture them, sitting near a fire, pointing up and wondering what that bright face was made of. To them it wasn't a rock, it was something alive, perhaps watching them in return. When the moon vanished into darkness, some cultures thought it had been eaten or wounded, and when it came back it was reborn. In a way they weren't wrong. The moon's light does die and return, though now we know it's simply sunlight playing a slow, predictable game with the Earth. Still, that pattern became woven into myth and memory. Even now, if you step outside on a clear night, you can see why they thought it was special. It doesn't blink like stars do, it glows steady and calm. Its light doesn't burn, it cools. It doesn't demand attention, it keeps it. And because it was the brightest thing in the sky, it became a canvas for imagination. Faces were drawn into it. Animals, deities, omens. Whole stories began and ended with the moon as the backdrop. When people started naming things in the sky, the moon was first. It was the original benchmark. Every other bright object was compared to it. That's why, even today, when we discover other worlds orbiting distant stars, we still describe them as having moons. It's our standard for companionship. Earth's moon is unusual in more ways than one. For a planet of our size, having such a large companion is rare. It's about 1/4 of Earth's diameter, big enough that the two bodies actually orbit a shared point in space located beneath the Earth's surface, not at its centre. In a technical sense, we and the moon are co-orbiting partners. It's a subtle detail, but one that makes Earth-Moon a kind of binary system. Most planets don't have that kind of balance. Jupiter's moons are massive, but Jupiter itself is so huge that even Ganymede barely nudges it. Our moon, by contrast, has genuine influence. It stabilizes Earth's axial tilt, keeping our seasons consistent over long stretches of time. Without that, our planet might wobble chaotically, tilting back and forth, plunging into unpredictable climates. The moon's steadying hand is part of why Earth has been habitable for so long. You could say our moon is not just a companion, but a guardian. Its pull slows Earth's rotation gradually, transferring some of our planet's spin into its own orbital distance. That's why the days are getting slightly longer over time. It's not enough to notice, just a couple of milliseconds per century. But it's a reminder that the dance between the two bodies is alive even now. Every tide that rises and falls, every wave that meets a shore, is an echo of that slow exchange. And though we usually think of the moon as passive, simply reflecting sunlight, it's anything but inactive in its influence. It shapes the rhythm of life on Earth, right down to the patterns of certain animals that feed, breed, or migrate by the lunar cycle. If you imagine being one of the first astronomers, those early stargazers with simple lenses in the 17th century, the moon would have been both familiar and shocking. Through a telescope, it wasn't smooth at all. It had mountains, craters, shadows. It looked scarred, as if something violent had happened to it. This realization changed everything. The moon wasn't a perfect heavenly sphere. It was a place, a world. That discovery quietly opened the door to the idea that other worlds might have moons too, and that those moons might also be worlds in their own right. When Galileo pointed his telescope toward Jupiter and saw 4 bright dots orbiting it, it must have felt like meeting a family you never knew existed. For thousands of years, Earth's moon had seemed unique. Suddenly it wasn't. The sky had companions upon companions, and once that door opened, humanity never stopped looking for more. Saturn soon revealed its own followers, and even the distant planets, Uranus, Neptune, and later Pluto, were found to have their own tiny attendants. Our moon had gone from being one of a kind to being one among hundreds. Yet somehow that didn't make it any less special. If anything, it deepened our sense of connection. Because seeing that every planet has its own moons reminds us that companionship seems to be a universal pattern. Solitude, it seems, is rare. Whether it's Mars with its 2 small captured rocks or Jupiter with its 90-odd moons, nearly every major world has something orbiting it, and that makes Earth's relationship to its moon feel even more intimate, because it's not loneliness that defines our place in space, it's relationship. Imagine for a moment being one of those early watchers long before telescopes, sitting by a fire under a cloudless sky. There were no city lights back then, no artificial glow to dim the stars. The moon's light was bright enough to cast shadows. You could walk by it. For those people, the moon wasn't a curiosity, it was part of life's structure. They planted crops by it. They told stories under it. They celebrated its phases because they matched the cycles of the world around them. And when they looked up at it, they probably felt something we still feel now, even if we dress it up in science. The comfort of presence. The reassurance that something is always there, always watching, always returning. The way we see the moon has changed countless times, but our fascination hasn't. When humans finally walked on its surface, the entire species seemed to hold its breath. That moment, that small figure stepping down onto the grey dust, was the first time life from Earth had touched another world. The image of the Earth rising above the lunar horizon, a blue marble hanging over a barren plain, did something to us. It flipped our perspective. Suddenly, we saw our world from the outside, small and fragile. The moon gave us that vantage point. It became a mirror that showed us who we are. But even after that giant leap, the moon remains more familiar than understood. We've brought back samples, we've mapped its surface in exquisite detail, yet questions linger. Why is the far side so different from the near side? Why did it cool unevenly? What can its craters tell us about the history of impacts that Earth endured, but forgot under erosion and oceans? The moon is like a diary kept by the early solar system, one that never got rewritten. Every crater, every ridge, is an entry in a history book 4.5 billion years long, and still, the moon is only one chapter in a much larger story. When we talk about moons in general, we're talking about a whole category of worlds, each with its own personality. Some are frozen solid, others hide oceans beneath their crusts. Some are volcanic, constantly remade by internal heat. Some are captured asteroids, little wanderers snagged by gravity. Some orbit close enough to be stretched by their planet's pull, others so far that they barely feel its tug. The diversity is astonishing, and yet they all share one thing. They move in circles around something larger than themselves. They exist in relationship. That's a comforting thought, especially in the quiet of night. Because as you sit here listening, perhaps half aware of your breathing, maybe your thoughts wandering a little, the same gravity that holds our moon in orbit is holding every moon in the solar system in place. It's the same force that keeps the planets turning around the sun, the same invisible thread that connects everything from dust to galaxies. We live in a universe bound by attraction, not just metaphorically, but literally. And moons are one of the clearest expressions of that law. They are evidence of connection written in motion. As we begin to move outward in our thoughts, past Earth, past our familiar grey companion, it's helpful to remember that what we call a moon can look very different elsewhere. When we reach Mars in our imagination, the two tiny shapes circling it hardly resemble our moon at all. They're irregular, pockmarked, small enough that gravity couldn't make them round. They look like captured debris, yet they play their part. They cast shadows, they tug slightly at Mars, they even contribute dust to its atmosphere. They remind us that even the smallest companions have influence. Each planet's moons tell a story not just about the planet, but about the solar system's history. They're like time capsules left behind from its formation. Some moons formed alongside their planets, condensing out of the same swirling disk of gas and dust. Others arrived later, captured by chance. Some were born from collisions, fragments that never escaped. Together they create a mosaic of how worlds grow, collide, and change. When you think about it that way, asking, how many moons are in our solar system, isn't really about counting objects, it's about counting stories. Even our language for them carries hints of affection. We say a planet has moons, as if they're possessions, though of course they belong to no one. We say they orbit their parent planet, a word that implies both loyalty and motion. And when we discover a new one, we give it a name, not a number, a name. Usually from myth or literature, but still, naming is a human gesture of recognition. We name things we wish to remember, things we care about, things we want to understand. Every new moon discovered gets drawn into that circle of attention, however briefly. As the centuries have passed, the number of known moons has grown faster than almost any other category of celestial object. In the early 20th century, we knew of only a few dozen. By the end of that century, hundreds. Now, with new telescopes and improved detection techniques, we add more almost every year. Some of the smallest may not survive long. They might collide or drift away. But the larger ones, the enduring companions, are the ones that keep astronomers awake at night, in the best possible way. Because each one might hold answers to questions far beyond its orbit. How life begins, how planets evolve, how water hides and moves in space. And yet, despite all that expansion, we keep returning to the same starting point. Our moon. It's still the model, the baseline, the one we know best. It's where our sense of companionship in the sky began. Every time a spacecraft photographs another world's moon, we instinctively compare it. Is it bigger or smaller than ours? Is it colder, more active, more mysterious? We measure all other moons against our own because it was the first one to keep us company, the first one to teach us that the universe doesn't do solitude for long. So here we are, sitting quietly beneath the same lunar glow that has touched every generation before us. Its light has reflected off the eyes of hunters, poets, sailors, astronauts, and now you. The same photons bouncing off its dusty plains travel down through your window, touch your skin, and fade. That gentle light is 8 minutes old from the sun and a little more than 1 second old from the moon. In that small stretch of time, the whole concept of distance and company shrinks. You are, in a literal sense, bathed in borrowed sunlight reflected from a world that orbits us, held steady by the same forces that hold galaxies together. The moon may not speak, but it's always answering the same question we keep asking the night. Are we alone? Its presence, and the presence of hundreds more like it around other planets, gives us the same answer over and over. No, nothing travels this vast universe entirely alone. Everything orbits something. Everything is bound to something else, however faint the pull. And that, perhaps, is why we find the question of moons so endlessly comforting. It's not just a curiosity about numbers or categories. It's a reminder that the cosmos, for all its emptiness, is full of connections. When you ask how many moons are in the solar system, the question sounds straightforward enough, like something a textbook should answer with confidence. But the deeper you look, the more it begins to unravel. The answer isn't just changing, it's slippery. Numbers keep moving, definitions blur, and what we once thought we knew starts to look temporary. It's like trying to count waves in the ocean. They're there, yes, and they follow patterns, but they're also constantly forming, merging, fading. The solar system's moons are like that, a family in flux. Even the word moon feels solid until you test it. Most people imagine something spherical, with craters and shadows orbiting a planet like Earth's moon. But many moons don't look anything like that. Some are jagged, potato-shaped, barely held together by their own weak gravity. Some are fragments of old collisions. Some were born alongside their planets. Others were snatched out of passing orbits, captured by chance. So when we try to count them, we have to ask first, what counts? Astronomers define a moon, or more formally a natural satellite, as any object that orbits a planet or a smaller planetary body rather than the Sun. That definition sounds fine, but even there exceptions lurk. What about objects that loop loosely around a planet for a few years before drifting off? What about ring particles, thousands of them, each tracing its own orbit, each technically a satellite, if you look at it from the right angle. When does a ring particle become a moon? At a few meters across, a few kilometers? Or does it need to be large enough that gravity pulls it into a round shape? The border is fuzzy, and like most things in astronomy, that fuzziness keeps growing the closer we look. When the first telescopes scanned the skies, we knew of exactly one moon, our own. Then in 1610, Galileo pointed his telescope toward Jupiter and saw 4 tiny points of light moving night after night: Io, Europa, Ganymede, and Callisto. He didn't just find moons, he found evidence that not everything in the universe orbited Earth. That discovery cracked open a door that would never close again. Suddenly, moons weren't unique. They were common, and soon Saturn was found to have them too. Mars joined later with 2, then Uranus, Neptune, and even tiny Pluto. The list kept expanding, and every time a better telescope came along, the number rose again. For centuries, astronomers could name the moons of the solar system on one hand, then on 2, then on all their fingers and toes. Now it takes entire spreadsheets to keep up. The largest planets have become almost absurdly rich in moons. Jupiter alone has more than 90 confirmed. Saturn recently overtook it with over 150, depending on which discoveries are officially verified. Together, those 2 planets host most of the moons in our solar system. Around them swarm hundreds of small, irregular companions, each captured long ago, each following a crooked path through the giant planet's gravity fields. At this point, counting them becomes a kind of ongoing census rather than a fixed fact. Astronomers use powerful telescopes to scan the space around planets, looking for faint moving dots. These surveys take weeks or months, and the results often trickle out slowly. Sometimes, a small object first spotted in 2010 isn't officially confirmed as a moon until years later, after its orbit is observed enough times to prove it's bound to its planet. It's a slow, careful process. One moon can be announced, then quietly removed later if it turns out to be a passing asteroid that just happened to wander close. So the number of moons isn't just changing, it's breathing, swelling and shrinking as we learn more. If you had asked the question in the mid-1800s, astronomers would have told you there were about 20 known moons. Ask again in the 1950s, and the number had grown to around 30. By the end of the 20th century, the total had passed 100. Today it's closer to 300, if you include the tiny irregulars and the moons of dwarf planets. And that number will almost certainly climb. Every new telescope, every new mission, adds a few more faint points to the list. Each discovery is like another grain of sand added to a beach we didn't know was endless. But it isn't just about more moons being found. It's about the rules changing underneath the count. When Pluto was reclassified as a dwarf planet in 2006, its 5 known moons didn't vanish, but they did move categories. They became part of a new conversation about what counts as a planet, and by extension, what counts as a moon. The same happened with smaller bodies like Eris and Haumea, each with at least one confirmed moon. Once, those would have been invisible to our questions. Now, they're included. The universe didn't change. We just learned how to see more of it. Even among the main planets, the distribution of moons tells a story about how the solar system formed. The inner planets, Mercury, Venus, Earth, and Mars, have very few. Mercury and Venus have none at all, likely because they orbit too close to the Sun for a small moon to survive its gravitational influence. Earth has 1, Mars has 2. But once you pass the asteroid belt, the number explodes. Jupiter, Saturn, Uranus, and Neptune each have dozens. It's as if the outer regions of the solar system, cold and less disturbed by the Sun's pull, became nurseries for moons. The gas giants didn't just attract gas and dust, they collected companions. Their gravity fields are vast, sprawling, capable of capturing stray objects that wander too near. Each capture becomes another moon. Some are long-term residents, others may only stay for a few million years before drifting away again. When scientists talk about these collections, they often divide the moons into two categories: regular and irregular. Regular moons orbit close to the planet, in the same direction it rotates, usually along its equatorial plane. These likely formed alongside the planet, condensed from the same disk of material. Irregular moons, on the other hand, tend to orbit farther out, often at steep angles, or even in the opposite direction of the planet's spin. These are the captures, the wanderers pulled in by gravity's reach. For every neat circular orbit, there are dozens of crooked looping ones. Counting them isn't just a matter of adding up numbers, it's like cataloguing history. Every moon, every orbit tells a piece of how the solar system assembled itself from chaos. When the planets were forming billions of years ago, collisions were constant. Disks of dust surrounded the growing worlds. Some fragments stuck together, some were thrown out, and some became trapped in orbit. Over time, those trapped fragments smoothed out into spheres, or at least lumpy ellipsoids, and became moons. Others remained jagged, the rough remnants of broken collisions. Some moons even have their own tiny moons, co-orbital companions that share the same paths, weaving in and out like dancers. Saturn's system is perhaps the most extreme example of this complexity. Its moons range from Titan, with its dense atmosphere and methane lakes, down to pebbles barely large enough to cast a shadow. Inside the planet's rings, countless small moonlets orbit, each helping to maintain the shape of the rings through their gravity. If you were to zoom in close enough, you might find thousands of these miniature worlds, each technically a moon, each influencing the next. So when someone says Saturn has 150 moons, that's really just a snapshot. The truth is more like a gradient, a continuum of companions from the grand to the microscopic. The real number is probably uncountable. Jupiter is no less impressive. Its 4 large Galilean moons are only the beginning. Beyond them, a swarm of smaller ones stretches far into space, grouped in clusters that share similar orbits and inclinations. These groups likely came from larger bodies that broke apart long ago, fragments of collisions that never left the planet's grasp. Some orbit in the same direction as Jupiter's rotation, others move backward, retrograde, captured from the outer reaches of the solar system. Every time we find another, it fits into this sprawling pattern, like a missing piece in a puzzle that's still being drawn. Even the smallest planets and dwarf planets contribute to the count. Pluto's 5 moons are all believed to have formed from a collision, similar to how our own moon came to be. Eris, the distant dwarf planet that sparked the debate over Pluto's classification, has 1 moon called Dysnomia. Haumea, known for its elongated shape, has 2. Makemake has 1 faint companion, discovered only recently. Each new detection pushes the boundary of what we consider part of the solar system's moon count. Somewhere out there, beyond even these known worlds, there may be more. Tiny bodies orbiting other dwarf planets we haven't yet identified. If there's a theme running through all of this, it's that the universe resists being tallied. Every time we think we've pinned down a number, we find out that the number was just a temporary marker. Counting moons isn't like counting marbles in a jar. It's like trying to count the ripples in a pond when the wind is blowing. They're constantly overlapping, changing, forming, fading. Some scientists even joke that the true number of moons in the solar system is however many you can find this week, and they're not far off. But there's a beauty in that uncertainty. It means the solar system isn't a finished diagram in a book. It's an evolving landscape. Each moon added to the list reminds us that exploration is still happening, not in some abstract future, but right now. When telescopes in Chile or Hawaii or orbiting observatories detect a new moving dot near a distant planet, that's a discovery in real time. That's someone watching the sky and realizing that a faint pixel of light has a story of its own. It's also worth remembering that these discoveries aren't just names on a list. They change how we understand gravity, planetary formation, and even the potential for life. Some moons have atmospheres, some have magnetic fields, some have oceans sealed beneath ice. By studying them, scientists learn how heat moves through planetary systems, how water survives, how chemistry evolves. Counting moons isn't about arithmetic, it's about mapping possibility. And if you step back far enough, you start to see another pattern. The more we find, the more it seems that every world, large or small, wants a companion. Maybe that's just gravity doing what gravity does, pulling things together, holding them in orbit. But it also feels like a kind of cosmic echo. No planet spins entirely alone. Even the lonely ones have stories written around them in faint trails of dust, in captured fragments, in invisible orbits. So when someone asks how many moons are there, the most honest answer might be, more than we knew yesterday, and fewer than we'll know tomorrow, because the solar system is still unfolding, still revealing itself piece by piece. The act of counting isn't about reaching the end of the list. It's about realizing that the list itself keeps growing, the way a tree keeps adding rings long after you've stopped looking. If you were to picture the solar system tonight, not as a set of static spheres, but as a living system, you might imagine it as a great spinning clockwork where each planet has a small cluster of followers moving with it, each moon tugging slightly on the next. From Mercury's empty space near the Sun to Neptune's distant orbit, every planet contributes its rhythm. Together they create a kind of celestial music, too slow for human ears, too vast for human instruments, but steady all the same. And somewhere in that quiet, in those orbits and counts and endless revisions, lies the reason we keep asking. Counting the moons isn't about the number itself. It's about finding our place in a system that refuses to stand still. It's about the comfort of knowing that even in the most distant corners, something is circling something else, following its path faithfully through the dark. As we move on from numbers and definitions, from the act of counting itself, we start to see that each of these companions deserves its own moment. Some are worlds so rich in mystery that they could fill lifetimes of study. Others are barely more than shadows, yet still part of the same grand pattern. When we talk about moons, there's one that always stands at the centre of our attention, not because it's the largest or the most unusual, but because it's ours. Every child who has ever looked up at a night sky has seen it. Every civilization has written its stories around it. It's both familiar and unreachable, ancient and yet freshly new every night. Earth's moon is so woven into our lives that we often forget it's a separate world. But if you could step back and look at Earth and its moon together, you would see two bodies locked in motion, circling each other endlessly, caught in a balance that has shaped everything about our planet and maybe even our existence. It's easy to think of the moon as a companion, but scientifically it's more than that. It's part of Earth's history written into orbit. About 4.5 billion years ago, not long after the planet itself had formed, something the size of Mars collided with Earth. It struck at an angle, a violent impact that vaporized rock and metal, flinging molten material into space. For a while, the sky must have glowed with debris, a ring of Earth's own substance encircling it. Over time, gravity gathered that material into a sphere. That sphere cooled, hardened, and became the moon. Every time you see it rise, you're looking at what's left of that ancient collision, a fragment of Earth that broke away but never left completely. In the early days, the moon was much closer. Tides were stronger, days were shorter, and nights were brighter. Slowly, over billions of years, it drifted outward, pushed by the same tidal forces it creates. Even now, it's moving away from us at roughly 4 centimeters per year, the rate your fingernails grow. It doesn't sound like much, but over time, it changes everything. A few 100 million years from now, total solar eclipses will no longer occur, because the moon will appear too small to cover the sun completely. The perfect symmetry we now enjoy when the moon and sun match in the sky is temporary, a fleeting alignment in cosmic time. For now, we happen to live in the rare era when they balance perfectly, and that coincidence has shaped more than just our view of the heavens. It has shaped our understanding of patterns, of cycles, of what it means for things to repeat and return. When you see the moon's light, you're seeing sunlight reflected off grey dust and rock. Its glow looks gentle, but the surface it comes from is harsh. A world without air, without weather, where day and night last for 2 Earth weeks each. When the sun shines there, temperatures soar to over 120 degrees Celsius. When darkness falls, they drop below minus 170. There are no sounds, no winds, no clouds. Only the slow passage of shadows across an endless landscape of stone. The silence isn't just quiet, it's total. The kind of silence that exists nowhere on Earth. That silence, preserved for billions of years, has made the moon a kind of time capsule. Because there's no atmosphere to erode or protect, everything that happens there stays. Craters from ancient impacts are as sharp now as the day they formed. Even the footprints left by astronauts half a century ago remain undisturbed, perhaps for millions of years more. If you were to stand on that surface and look back toward Earth, you would see something extraordinary. A blue and white sphere suspended against a black sky. It wouldn't rise or set because the moon's rotation is locked to its orbit. The same side always faces Earth, a phenomenon called tidal locking. From our perspective, we always see the same lunar face. From the moon, Earth hangs still in the sky, rotating but not moving across the horizon. You could watch clouds swirl, storms bloom, continents drift slowly in view. You could see day and night roll across the planet, lightning flashing in tiny bursts. For astronauts who have seen it, that sight was often described as overwhelming. To stand on another world and watch Earth, not as a map, not as a concept, but as a distant glowing world, changes something fundamental in how we think about home. Back on Earth, that same moon has shaped far more than our imagination. Its gravity pulls on our oceans, creating tides that rise and fall twice each day. Without it, the tides would be weaker, more influenced by the sun, but less dynamic. That gentle rhythm of the sea has influenced life since the earliest forms crawled onto land. The ebb and flow of water create changing environments. Tidal pools that fill and empty, coasts that transform daily. Many evolutionary paths likely began in those shifting zones. In a very real way, the moon's gravity helps shape the biology of Earth itself. It's hard to imagine the planet's history without that steady tug. Even our sense of time owes something to it. Ancient calendars were lunar before they were solar. Months, literally derived from the word moon, began as ways to track its phases. The first clocks humanity ever used were made of light and shadow, cast by that orbiting sphere. For countless cultures, the moon wasn't just a light in the sky, it was a companion that reflected human experience. In its cycles, people saw life and death, beginnings and endings. When it waxed, it symbolized growth and renewal. When it waned, rest and decline. Festivals, rituals, and agricultural schedules followed its rhythm. In some languages, the word for month and moon are still the same. In others, the moon was tied to myths of gods, lovers, and lost time. The Chinese told of Chang'e, who drank an elixir of immortality and floated up to live forever on the moon. The Greeks imagined the goddess Selene driving her chariot across the night sky. The Maori saw it as a symbol of fertility and rebirth. Even now, people still name the full moons, harvest moon, wolf moon, strawberry moon, as if each one has its own personality. Science has explained the mechanics, but not the feeling. The moon remains emotional, not just astronomical. When humans finally left Earth to walk on it, that emotion was still there. The Apollo missions were feats of engineering, but also of imagination. The first landing in 1969 was the culmination of centuries of wondering. Watching that small craft touch down, seeing a person descend onto another world, wasn't just a technological triumph, it was a human one. The first footprints on the moon are as symbolic as they are physical. They marked a moment when humanity extended its reach, not to conquer or claim, but simply to touch. The astronauts described the experience in plain, almost quiet terms. They spoke of the view, of the stillness, of how the Earth looked so fragile and whole from that distance. Some said it felt like looking at a living being. Others said it made borders and division seem meaningless. From that perspective, there were no countries, no politics, just one small, bright world hanging in a sea of black. The moon has always reflected our curiosity. Every new mission to it reveals something different, not just about the moon itself, but about how we think of exploration. In the early 2000s, new satellites mapped its surface in detail, showing deposits of water ice in shadowed craters near the poles. That discovery changed everything. The moon, once thought to be dry and lifeless, had traces of one of the essential ingredients for life, and a resource that could support future explorers. Now, new missions plan to return, not just to visit, but to stay. Space agencies are designing habitats, mining systems, and telescopes that might one day sit on its far side. The moon, it seems, is no longer just a destination. It's becoming a stepping stone, a quiet outpost on the path to deeper space. Yet even with all that technology and ambition, the most striking thing about the moon is still its presence. It's always there, constant but changing, reliable but never the same. Its light reaches every corner of the planet, falling on mountains, oceans, cities and fields alike. It has no preference, no bias. It illuminates equally. In its simplicity, it links everyone who has ever looked up. A person standing on a beach 1,000 years ago saw the same light you see tonight. That continuity is rare. Everything else changes. Languages, borders, cultures, even coastlines. But the moon's rhythm endures. Its orbit doesn't care for human calendars, but our calendars depend on it nonetheless. There's also a strange intimacy in how close it feels. It's about 384,000 kilometers away, far beyond reach for most of history, yet close enough to see with the naked eye. Its craters have names, its shadows are familiar. You can trace its outline through thin clouds, even during the day. It's the only celestial body where human footprints exist. And though robotic probes have travelled farther, nothing else in the sky feels quite as personal. The moon is, in a sense, the first reminder that the universe isn't separate from us. It's connected. Its light is the sun's, but its glow is ours. What's remarkable about the moon is not just what it does, but what it allows. Without its stabilizing influence, Earth's tilt would vary wildly, perhaps making climate swings too extreme for life to adapt comfortably. Without its pull, tides would weaken, ecosystems would shift, and the subtle synchronization between land and sea might break. Even the length of our days and the pace of Earth's spin have been molded by its presence. Over billions of years, the moon has been gradually slowing Earth's rotation, trading that energy for distance. Every day that passes is about 2 milliseconds longer than it was a century ago because of this slow exchange. Time itself, in the way we measure it, is being stretched by the moon. But for all its influence, it's a quiet force. The moon doesn't roar like storms or erupt like volcanoes. It simply moves, unhurried, in its endless orbit. And that patience has made it a symbol of calm for as long as people have watched it. Artists paint it, poets write about it, and astronomers measure it, all drawn to the same steady rhythm. It's the only world that affects every person on Earth without making a sound. The pull it exerts is invisible but felt, in tides, in sleep cycles, in moods, in memory. People say they feel different under a full moon. Science may not find evidence for that, but the feeling persists, maybe because it's the one time the night feels full, the darkness softened by light. When you trace the moon's phases, you're watching geometry unfold. Half of it is always lit by the sun, but from Earth, we see that illumination change as it moves around us. From new moon to crescent to half, to full and back again. That slow transformation is a reminder that change doesn't always mean loss. The moon never disappears. It just turns away, then returns. In that cycle, there's something steadying, a quiet rhythm that mirrors breathing, seasons, and even thought. We often think of space as cold and distant, but the moon makes it feel personal, immediate. It brings the cosmos close enough to see from your backyard. If you could speed up time and watch Earth and the moon together, you'd see something mesmerizing. Two spheres spinning around a shared center of mass, locked together in motion. The Earth would wobble slightly, the moon would glide, and together they would trace an endless spiral around the sun. It's a reminder that our world doesn't travel alone. We are part of a system within a system, orbiting and being orbited, held by the same gravity that binds everything else. And just as the moon orbits Earth, Earth orbits the sun, and the sun moves through the galaxy, which itself drifts through the cosmos. The same pattern repeats everywhere, motion around motion, connection within connection. That's what makes the moon faithful, not in a sentimental sense, but in the literal one. It keeps its orbit, keeps its rhythm, keeps its place. Through every season, every tide, every history we've written, it's been there, doing the same quiet work. It doesn't fade, it doesn't hurry, it just circles. And in that motion, it teaches us something simple about endurance. That constancy can exist even in movement, that stability doesn't mean stillness. The moon is always moving, yet it's always there. As we look beyond it, past our own skies toward the other planets, we'll find that Earth's situation is almost modest. Our single moon is special, but it's also solitary. Out there, other worlds are surrounded by dozens of companions, entire miniature systems of their own. They make our relationship with the moon look almost quiet in comparison. But before we leave it behind, it's worth pausing to recognize that everything we've learned about moons, about orbit, gravity, and companionship, started here, with this one. It's our template, our first example, our guide for understanding all the others. When you leave Earth in thought, the first world you encounter is Mars. It's close enough to feel familiar, far enough to feel foreign. People have looked at it for centuries and seen a kind of mirror, a smaller, colder version of home. Its deserts resemble our own, its polar caps grow and shrink like Earth's do, and its reddish colour makes it seem alive even though it's quiet. But Mars doesn't travel alone. It too has companions. Not grand ones like Jupiter's, not bright or majestic, but two small, almost unnoticed shapes that hurry around it in silence. They are Phobos and Deimos, Mars's moons, its faint shadows in orbit. When you first see them in photographs, they don't look like moons at all. They look like broken stones, rough and uneven, full of craters. Their names come from Greek mythology, Phobos meaning fear, Deimos meaning terror, the twin sons of Ares, who was the god of war. The names fit Mars, known since ancient times as the Red Planet, a symbol of conflict and fire. But these two moons don't look fierce. They look fragile. They seem more like survivors than warriors, caught by chance rather than born in place. Scientists believe they were once asteroids that drifted too close to Mars and were captured by its gravity. If that's true, then they are ancient visitors, relics of the solar system's early chaos, held there ever since. Phobos, the larger of the two, is still tiny compared to our moon, only about 22 kilometers across. Deimos is even smaller, around 12. You could walk across their surfaces in a few hours. Their gravity is so weak you could jump and never land again if you weren't careful. They are not spheres but lumpy, irregular chunks, shaped by collisions and fractures. Each one is covered in craters, streaks, and grooves. Their surfaces are made of dark rock mixed with dust so fine it moves like smoke. Sunlight barely reflects off them, giving them a dull, ashen appearance. From the Martian surface, they don't look large enough to dominate the sky. Phobos rises and sets quickly, racing overhead twice each Martian day. Deimos moves more slowly, taking nearly 3 days to complete its circuit. Together they give Mars a restless rhythm, one moon rushing past, the other lingering behind, both casting faint shadows across the red plains. Phobos orbits extremely close, so close that it moves faster than Mars itself rotates. To someone standing on the Martian surface, Phobos would rise in the west and set in the east, appearing to move backward compared to the Sun. It circles Mars every 7 hours and 39 minutes. You could watch it cross the entire sky in a single afternoon. It's so close that Mars's gravity is slowly pulling it inward. Each century it drops a few centimeters closer to the planet. Someday, maybe in 50 million years, it will fall apart under tidal stress, forming a thin ring of dust around Mars before finally raining down in fragments. Deimos, in contrast, is moving away, inching outward over time, the same way our moon drifts from Earth. The two moons are heading in opposite directions, one doomed to fall, the other slowly escaping. Mars's companionship, it seems, is temporary, its moons destined to change or vanish. If you could stand on Phobos and look back at Mars, the view would be immense. The planet would fill almost half the sky, glowing rust red with shadows of canyons and volcanoes. The horizon would curve sharply, the faint sunlight spilling across its ridges. You'd see dust storms swirling far below, maybe even the glint of sunlight reflecting off ice near the poles. There would be no sound, no wind, only the faint vibration of the moon's slow motion as it circles its parent world. From that vantage point, you'd understand why astronauts and dreamers have long been fascinated by Mars's moons. Not because they are beautiful, but because they remind us how fragile orbits can be, how easily gravity catches and holds and then lets go again. Phobos is covered with grooves that run across its surface like scars. Some of them were caused by impacts, others by the stress of tidal forces as Mars pulls on it, slowly tearing it apart. Its most prominent feature is Stickney Crater, a huge depression that covers nearly half its width. The impact that formed it nearly destroyed Phobos, but somehow it held together. That crater, with its streaks of ejecta radiating outward, gives Phobos a distinct battered face, a reminder of how violent the solar system's history has been. Deimos, on the other hand, is smoother and less scarred, perhaps coated with more dust from its own surface breaking down over time. Its orbit is nearly circular, calm and steady, a quiet contrast to Phobos's restless speed. Together they form a kind of balance, one rough and near, one smooth and far, a microcosm of motion and endurance. Mars itself shapes their lives constantly. Its thin atmosphere doesn't reach them, but its gravity dominates everything they do. Every orbit, every shadow they cast is a trace of that invisible pull. When they pass in front of the Sun as seen from the Martian surface, they create brief, partial eclipses, not total, because they're too small, but enough to dim the light for a few moments. Rovers like Spirit, Opportunity and Curiosity have captured these events with their cameras, watching the Sun flicker as Phobos slides across it. Those moments are tiny reminders that Mars has its own version of lunar cycles, its own celestial timing. They might not shape tides or calendars the way Earth's moon does, but they give the red planet a rhythm, a steady mark of passing time. The story of how these moons came to be captured is still being studied. One theory says that Phobos and Deimos are remnants of a larger moon that once orbited Mars but was shattered by an impact. Another suggests they were asteroids from the nearby asteroid belt that happened to fall into the right gravitational window. Capturing an asteroid isn't easy. It requires a delicate balance of speed, direction, and timing. Most pass by too quickly to be caught, but if conditions are just right, a planet's gravity can slow them down enough to trap them in orbit. It's a rare coincidence, a product of luck and physics intertwined. That makes Mars's moons not just companions, but cosmic accidents, fragments of wandering rock that found a home, however temporary. Phobos and Deimos also hint at the transitional nature of the solar system. They are somewhere between moons and asteroids, part of both categories and fully belonging to neither. They have the irregular shapes and rocky composition of asteroids, but they live as moons, bound to a planet's gravity. They show how blurred the lines can be in space, how one object can shift identity depending on where it drifts. If Phobos and Deimos had passed a little closer to Jupiter, they might have become part of that giant swarm of outer moons instead. If they had stayed free, they'd still be anonymous rocks moving through the asteroid belt. Instead, they orbit Mars, transforming from wanderers into companions. For scientists, these small moons are more than curiosities. They may hold clues about Mars's early environment and the material that built the planets. Their surfaces contain carbon-rich compounds and minerals similar to those found in certain asteroids. By studying them up close, researchers hope to understand how rocky planets collected their ingredients, the metals, the silicates, the water-bearing materials that made Earth possible. There are even plans to visit them again. The Japanese space agency, JAXA, has developed a mission called MMX, Martian Moons Exploration, which will send a spacecraft to orbit Mars, land on Phobos, collect samples, and bring them back to Earth. When that happens, we'll be holding pieces of another world's moons in our hands for the first time, small fragments of Mars's fleeting shadows. Phobos and Deimos also raise questions about the future. When Phobos eventually falls apart, its debris may spread into a thin, glowing ring around Mars. Imagine looking at Mars then, with a pale, dusty halo surrounding it, like a memory of a moon that once was. That transformation, from moon to ring, is part of the solar system's ongoing change. Moons are not eternal. Some collide, some break apart, some drift away. In their slow evolution, we can see time working not as a straight line, but as a cycle of creation and decay. Every orbit, every fall, every capture is a version of the same story repeating across billions of years. Mars's moons are humble next to the giants we'll soon meet, but they hold a certain charm because of their impermanence. They remind us that companionship in the cosmos doesn't always last forever. Some relationships end not in distance, but in collapse. And yet, even that ending becomes something new. A ring, a pattern, a trace of what once was. In that sense, Phobos and Deimos aren't just moons, they're symbols of the solar system's ongoing motion. Everything changes, but nothing truly disappears. It just finds a new orbit, a new form, a new way of being connected. When you picture Mars with its two small attendants, it's easy to feel a kind of sympathy for it. It doesn't have the grandeur of Jupiter's moon family, or the serene balance of Earth's single companion. Its moons are little more than captured fragments, rushing endlessly around a planet that once might have had rivers, oceans, and air. Yet, even now, with its thin atmosphere and frozen deserts, Mars isn't completely alone. Those two pieces of ancient rock, barely large enough to cast proper shadows, follow it faithfully through its long orbit around the Sun. They're not steady in the way Earth's moon is, but they're present. They orbit. They endure for now. And maybe that's all companionship in space ever really means. Not permanence, just persistence. If you were to stand on Mars at dusk and watch the sky, you might see Phobos rising fast, moving so quickly that it crosses the horizon in a matter of hours. Its light would be faint, its path low, but it would draw a line of motion across the red twilight. Later, you'd see Deimos far away, gliding slowly, steady and calm, as if balancing its brother's haste. Together they would move in a rhythm only Mars knows, and as the planet spins beneath them, dust storms swirling, wind carving the same rocks again and again, two moons would continue their orbits, quiet, unchanging in their pattern, even as they slowly drift toward different fates. When you move past Mars, the solar system begins to change character. The space between worlds grows vast, and sunlight softens into something thin and distant. It takes longer to reach everything out here, and what it touches no longer glows with warmth, but with reflection. Beyond the asteroid belt lies a world so immense that it dominates this entire region. Jupiter. It isn't just another planet, it's the gravitational anchor of almost everything around it. Its pull shapes the orbits of asteroids, influences the paths of comets, and guards the outer system like a silent monarch. And as every monarch has a court, Jupiter has one too. An immense entourage of moons, each one moving to its gravity, each one part of the intricate structure that surrounds this giant. When Galileo first saw them through his small telescope in 1610, he couldn't have known how many more there would be. He saw 4 bright points of light circling Jupiter, shifting their positions from night to night. He called them Medicean stars to honour his patrons, the Medici family. But those 4 moons, Io, Europa, Ganymede and Callisto, became known as the Galilean satellites. They were the first worlds ever discovered orbiting something other than Earth, and that discovery quietly rewrote our place in the cosmos. It showed, in direct evidence, that not everything revolved around us. The universe was larger, more complex and filled with systems within systems. Those 4 moons still remain the heart of Jupiter's domain, though they are now joined by dozens upon dozens of smaller companions, over 90 that we've confirmed so far, with more waiting to be verified. If Earth and Mars are modest in their companionship, Jupiter is the opposite. It gathers moons the way the sea gathers shells. Some are ancient, formed alongside the planet. Others are wanderers, captured from the outer reaches of the solar system. Some are large enough to be considered planets in their own right, while others are no more than a few kilometers wide, barely visible against the background of space. Together they make Jupiter a miniature solar system, a model of what the early formation of worlds might have looked like. The scale of it is staggering. Jupiter itself could fit more than 1,000 Earths inside it. Its magnetic field stretches millions of kilometers, and its gravity dominates a region that could swallow entire planetary systems. Within that gravity, its moons move in elaborate harmony, like a vast celestial dance that's been continuing for billions of years. Each orbit influences the next. Each moon's motion tugs subtly on its neighbours, setting up resonances that shape their paths and even their geology. It's not chaos, it's structured movement, like music written in the language of gravity. The innermost of the 4 Galilean moons, Io, is a world of fire. It looks deceptively small and simple at first, a golden sphere covered in spots and streaks. But those colours come from sulfur compounds, and those streaks mark volcanoes. Io is the most volcanically active world in the solar system. Its surface is constantly changing, reshaped by eruptions that throw molten material hundreds of kilometres into the sky. The reason for all that activity is tidal heating. Jupiter's immense gravity, combined with the gravitational pulls of Europa and Ganymede, stretches and flexes Io as it orbits. That constant flexing generates heat deep inside, melting rock into magma. Where Earth's volcanoes are separated by continents, Io's cover nearly the entire planet. There are hundreds of them, each one a vent into a restless interior. It's a world that never stops remaking itself. Every orbit leaves it a little different, its surface always young, always new. Just beyond Io lies Europa, smaller, smoother, and infinitely more mysterious. Where Io burns, Europa freezes. Its surface is a shell of water ice, smooth except for long cracks that trace it like veins. Beneath that shell lies something extraordinary, an ocean, a vast body of liquid water kept from freezing solid by the same tidal heating that makes Io boil. That hidden ocean may contain more water than all of Earth's combined, and where there is liquid water, there is the potential for life. For decades, scientists have dreamed of what might swim beneath Europa's frozen crust. Perhaps microbial life, perhaps something more complex, nourished by chemical energy from the ocean floor. The idea is not fantasy, It's one of the strongest possibilities for extraterrestrial life in our solar system. The Europa Clipper mission, currently being prepared, will explore it in detail, flying close again and again to map its surface and measure its chemistry. If anything alive exists there, even the simplest microbe, it would be one of the most profound discoveries in human history. Farther out still is Ganymede, the largest moon not only of Jupiter, but of the entire solar system. It's bigger than Mercury, and it has its own magnetic field, a rarity for a moon. That field interacts with Jupiter's, creating auroras that ripple in its thin atmosphere. Its surface is a mix of dark, ancient regions and lighter bands, where tectonic forces have reshaped the ice. Beneath that icy crust there may also be an ocean, deep, buried under layers of frozen material, perhaps containing salt and minerals. Ganymede is like a world that never became a planet, frozen in a middle stage of development. If it orbited the Sun instead of Jupiter, it would be a world of its own, with an atmosphere and maybe even weather. But here it remains a moon, orbiting quietly in the glow of its parent planet's immense magnetosphere. The outermost of the Galilean moons, Callisto, is a relic of deep time. Its surface is the most heavily cratered of any in the solar system. Every impact it has ever suffered is still visible. It's a geological record stretching back billions of years, untouched by internal activity. Unlike its siblings, Callisto doesn't show signs of tidal heating. It's too far from Jupiter for those forces to reach it strongly. Its interior is cold, stable, and layered. Ice and rock mixed together. Yet even here, far from the volcanic fire of Io and the icy oceans of Europa, there may still be hidden complexity. Data from spacecraft suggests that Callisto too may hide a subsurface ocean. If so, it means that 3 of Jupiter's 4 great moons could harbour liquid water beneath their surfaces. In the cold outer solar system, water is not rare, it's a foundation. These 4 great worlds, Io, Europa, Ganymede, and Callisto, form a system within a system, each linked to the next through resonance. Io orbits Jupiter 4 times for every 2 of Europa's orbits and every one of Ganymede's. This gravitational rhythm keeps their orbits slightly elliptical, maintaining the internal heating that powers their dynamic geology. It's a pattern of balance and tension that has lasted since the early days of the solar system. And beyond these 4, the court continues. Outside their orbits lie dozens of smaller moons grouped into families. Some move in circular paths, regular and aligned with Jupiter's equator. Others travel in tilted, elongated, or even retrograde orbits, moving backward compared to the planet's rotation. These irregular moons are likely captured objects, pulled from the asteroid belt or beyond. They orbit far from Jupiter, some tens of millions of kilometers away, forming clusters that share similar inclinations and distances. Each cluster may be the fragments of a single body broken apart by collision. They are the leftovers of ancient events, preserved in slow motion. One of these small moons, Amalthea, sits close to Jupiter's clouds, bathed in radiation. It's oddly shaped, reddish and porous, perhaps a loosely held pile of rock rather than a solid sphere. From its surface, Jupiter would dominate the sky, filling it almost entirely. Sunlight would be dim compared to the planet's glow, and the vast bands and storms of Jupiter's atmosphere would roll endlessly across that view. For all their size, Jupiter's small moons live in harsh conditions. Radiation, meteoroid impacts, and gravitational stress constantly alter them. Some might even crumble over time, feeding Jupiter's faint ring system. The idea of Jupiter having rings surprises some people, but it does. They are thin, faint, and dusty, made mostly of material from micrometeorite impacts on its moons. They form a halo around the planet, invisible to the naked eye but captured beautifully by spacecraft. Those rings are part of the same story. Everything around Jupiter exists in relationship, exchanging material, energy, and motion. Even the smallest grains orbit with purpose. For a planet of Jupiter's scale, companionship isn't optional. Its gravity is so powerful that anything passing too near becomes part of its system. Over time, it has collected and shaped a vast family of moons, each one contributing to the planet's complexity. If you could see them all at once, not just the big four, but every small rock and fragment, the space around Jupiter would look crowded. Thousands of orbits overlapping, weaving patterns that never repeat exactly, but always remain stable. From a distance, that motion would look slow and graceful, but up close, it's precise and constant. Jupiter's system also tells us something about the early solar system itself. When the planets were forming, the giant worlds acted as gravitational wells, capturing or deflecting much of the debris left over from creation. Without them, the inner planets might have been bombarded into ruin. Jupiter, in a sense, acted as a shield, drawing comets and asteroids toward itself and away from Earth. Its immense gravity probably changed the course of our planet's history before it even began, and within that same gravity, the moons of Jupiter evolved into the diverse system we see today. The beauty of Jupiter's moons lies not only in their variety, but in how they reveal connections between physics and imagination. Every one of them shows a different expression of the same natural laws. Io turns gravity into heat. Europa turns that heat into potential life. Ganymede turns it into magnetism. Callisto turns its absence into stillness. It's a reminder that the same forces can create wildly different outcomes, depending on context and distance. That variation, that adaptability, is part of why the solar system feels alive even in its silence. When spacecraft like Voyager, Galileo and Juno flew by or orbited Jupiter, they gave us glimpses of this immense system. They showed volcanoes erupting in real time, plumes of water bursting from cracks in ice, and landscapes that looked both alien and strangely familiar. Some of the images still look unreal, as though painted rather than photographed. They remind us that the solar system isn't uniform. It's textured, layered, and dynamic, full of worlds that would each be astonishing on their own. Jupiter simply happens to host many of them at once. From a distance, the planet's appearance is hypnotic. Bands of white, beige, and rust swirl in constant storms. The Great Red Spot, a storm larger than Earth, has been raging for centuries. Beneath those clouds lies a world without a solid surface, a massive ocean of hydrogen and helium growing denser toward the core. The pressures there are so great that hydrogen may exist as a metallic liquid. Lightning flashes through the upper atmosphere, sometimes illuminating the night side with brief, silent bursts. All around it the moons move, each orbiting at its own speed, each marking time differently, but all bound to the same gravitational song. If you were to stand on one of those moons, say Europa, and look up at Jupiter, the sight would be overwhelming. The planet would dominate the sky, filling it from horizon to horizon. Its cloud bands would move visibly in real time. You could see its shadow cast on other moons as they passed behind it. Every hour would bring new alignments, eclipses and shadows sliding across its surface. Time would feel slower there, not because it is, but because everything moves on such a grand scale. You would feel, perhaps for the first time, how vast and intricate a planetary system can be. Jupiter's moons are a reflection of its gravity, but they're also a reflection of diversity itself. Within one planet's reach exist worlds of fire, ice, water, and stone. Some glow, some freeze, some crack open with energy. Together, they represent almost every type of environment the solar system can produce. And that makes Jupiter not just a planet with moons, but a gallery of possibility. Beyond Jupiter's realm lies a world of balance and design so subtle that it feels almost deliberate. If Jupiter's system is a celebration of abundance, Saturn's is a study in elegance. It's the planet people recognize at a glance, the one wrapped in rings, shining softly against the black of space. Even before spacecraft visited it, Saturn's beauty was legendary. Through a small telescope, those rings appear as delicate arcs of light, smooth and unbroken. but up close, they become something else entirely. A vast system of ice and dust, thousands of individual bands, each made of countless pieces orbiting in perfect coordination. Saturn is often described as the jewel of the solar system, and that's not exaggeration. Its pale gold atmosphere, streaked with faint bands, glows with reflected sunlight. Its rings catch that light and scatter it in every direction, creating a halo that changes with the angle of the sun. From afar it looks peaceful, but it's also enormous, 9 times wider than Earth, with a mass so great that its gravity commands more than 150 moons and moonlets. Together, they make up a system even richer than Jupiter's but subtler, layered with fine details that reveal themselves only with time. When the spacecraft Cassini arrived at Saturn in 2004, it transformed our understanding of this planet. For 13 years it orbited the giant world, sending back images that changed how scientists and the public alike saw it. What had looked like a smooth ring turned out to be a complex living structure. The rings are made mostly of water ice, bright, clean, and surprisingly reflective. They extend more than 280,000 kilometers from Saturn's surface, but are rarely thicker than 10 meters. Each particle, from tiny grains to chunks the size of houses, follows its own orbit, colliding gently with others, spreading out, clumping again. They are like a river of frozen time, flowing endlessly around the planet. Between those shimmering bands move small moons, some only a few kilometers wide. These are the shepherds, moons whose gravity keeps the rings in shape. As they orbit, they gather material, carve gaps, and maintain boundaries. Without them, the rings would blur into each other, losing definition. You can think of them as caretakers, maintaining Saturn's most famous feature. Some of these shepherd moons, like Prometheus and Pandora, trace the edges of the F-ring, tugging on it gently and creating ripples that travel around the planet. Others, like Pan and Daphnis, live inside the gaps themselves, their tiny gravities sculpting sharp edges in the surrounding material. They are the hidden children of Saturn's rings, small, almost invisible, but vital to the balance of the system. Each moon and ring particle around Saturn exists in a delicate compromise between attraction and motion. Too close, and a moon would be torn apart by tidal forces. Too far, and it would drift away. The boundary where this happens is called the Roche limit. Inside that limit, large bodies cannot hold themselves together. That's likely how the rings formed, from a moon that came too close and was pulled apart. Its fragments spread into orbit, gradually flattening into the thin, bright structure we see today. Over time, collisions between icy particles ground them down into smaller pieces, creating the fine dust that gives the rings their glow. The process is slow and continuous. Even now, Saturn's gravity is shaping and reshaping them, keeping them in a kind of perpetual renewal, but the rings aren't static. They may not last forever. Observations suggest that they're slowly disintegrating, their particles spiraling inward under the drag of Saturn's magnetic field and atmosphere. Some of that material falls onto the planet as what scientists call ring rain, a steady drizzle of water and dust disappearing into the clouds. In hundreds of millions of years, the rings may thin and fade, leaving behind only faint traces. What we see today is a temporary moment in Saturn's long life, a phase of brightness between darker epochs. It's a humbling thought. The most recognizable feature of one of the solar system's greatest worlds might be fleeting. Beyond the rings themselves lie Saturn's larger moons, a collection so diverse it feels like a catalogue of planetary types. The largest of them, Titan, stands apart from all the rest. It's the second largest moon in the solar system, bigger than Mercury, and it has an atmosphere thicker than Earth's. For centuries, Titan was just a point of light, its surface hidden beneath orange haze. When the Cassini spacecraft and its companion probe Huygens arrived, that changed. The probe descended through Titan's atmosphere and landed softly on its surface, the first time humanity touched a world beyond Mars. What it saw was astonishing. There were rivers, lakes, and rain, but not of water. Titan's temperature is so cold that water is rock hard. The liquid flowing across its plains is methane and ethane, hydrocarbons that behave like water does on Earth. It rains methane. It fills lakes and carves valleys. There are clouds, storms, and changing seasons. It is in many ways a world that mirrors our own, except its chemistry runs in a different direction. Beneath Titan's crust lies another surprise, an ocean of liquid water mixed with ammonia, kept from freezing by internal heat and tidal forces. That means Titan, like Europa and Ganymede, may also harbour the potential for life, even if it's life unlike anything we know. Its atmosphere is rich in organic molecules, the same kinds that once seeded Earth's early chemistry. Every new image and data set from Cassini made Titan feel less like a moon, and more like an alternate version of a planet, one that chose a different path. It's the kind of place that keeps scientists awake at night, not because it's dangerous or alien, but because it feels eerily familiar in its differences. Then there's Enceladus, small, bright, and almost perfectly white. It's only about 500 kilometers across, but it has become one of the most important worlds in the search for life. When Cassini passed near it, it discovered something unexpected. Jets of water vapor and ice shooting from cracks near the moon's south pole. These plumes extend hundreds of kilometers into space, forming a thin, misty halo around Enceladus and feeding material into Saturn's E-ring. Inside those plumes, scientists found organic molecules and hints of salts, signs of a subsurface ocean warmed by tidal flexing. That means Enceladus, despite its size, has liquid water beneath its frozen crust, kept warm by the push and pull of Saturn's gravity. It's another reminder that life may not need sunlight or air to exist, just energy, chemistry, and water. The rest of Saturn's moons each add their own detail to this intricate system. Mimas, shaped like a cracked sphere, carries a massive crater that makes it resemble an eye staring into space. Tethys, Dione, and Rhea are icy worlds marked by fractures and ancient impacts. Some may have hidden oceans of their own. Others, like Iapetus, are half bright and half dark, their surfaces coated with contrasting materials that make them look split in two. Iapetus's equator is lined with a mountain ridge stretching for more than 1,000 kilometers, a feature unlike anything else in the solar system. Every moon here tells a slightly different story about how gravity and time sculpt worlds. Even the smallest fragments have a role. Tiny moons called ringlets drift along the edges of the rings, shaping them with their gravity. Some moons share orbits, 2 or 3 moving in lockstep, swapping places every few years in a gravitational dance. Others orbit at strange inclinations, tilted far above or below the ring plane. Together, they form a structure that's more like a symphony than a system, each part contributing to a larger harmony. Cassini's long mission allowed us to watch these movements unfold, to see the rings ripple as moons passed nearby, to watch shadows sweep across the planet's cloud tops as the seasons changed. The planet itself, immense and cold, is less solid than its appearance suggests. Like Jupiter, Saturn is mostly hydrogen and helium, with no clear surface, just layers that become denser with depth. Its winds reach speeds faster than any on Earth, and its poles host vast storms shaped like geometric patterns. The North Pole, in particular, is famous for its hexagon, a persistent cloud formation so large it could fit several Earths inside. The rings cast shadows on that atmosphere, faint lines of dusk stretching thousands of kilometers. It's a planet of subtleties, where light, shadow, and motion interact endlessly. When you think about Saturn's rings, it's tempting to see them as symbols of perfection, smooth, eternal, unchanging. But their reality is dynamic. They are collisions and cooperation made visible. Each particle traces its own path, yet together they create a single image. They are like the solar system's memory, a record of destruction turned into beauty. The moon that broke apart to form them no longer exists, but its fragments still circle the planet, reflecting sunlight into space. They've turned loss into structure, chaos into order. That's the quiet lesson Saturn offers, that even in the immense silence of space, motion can create grace. If you were to stand on one of Saturn's moons, perhaps Rhea or Dione, and look up, the sight would be indescribable. The rings would stretch across the sky, arching from horizon to horizon. They would not look solid, but luminous, shimmering like mist in sunlight. You might see small moons casting shadows onto them, their movements slow but steady. The planet itself would fill half the sky, pale and immense with storms swirling beneath its hazy atmosphere. The light would be soft, filtered by distance. Time would feel slower, not because it moves differently, but because every motion seems to happen on a scale too vast to rush. Saturn's system is not isolated. It's connected to everything that came before and everything that lies beyond. Its gravity interacts with Jupiter's, shaping the outer asteroid belt. Its moons share compositions with those farther out. It's a bridge between the warm, active worlds closer to the Sun and the colder, more distant realms of Uranus and Neptune. Every spacecraft that has passed by, Pioneer, Voyager, Cassini, has shown that this is not just a planet but an ecosystem of motion. Each piece matters, from the giant Titan to the smallest ring particle. And though the rings may fade in the future, their story won't end. The material will fall into Saturn, altering its atmosphere, becoming part of the planet itself. The cycle will continue, just as it always does in space. Creation, transformation, renewal. What Saturn gives us is perspective. It shows that even destruction can lead to beauty, that orbits can balance chaos into harmony, and that no part of the universe exists in isolation. Everything is connected by gravity, by time, by motion. The rings and their hidden children are not separate from the planet. They are extensions of it, the visible edges of its influence. And when you look at them through a telescope or a photograph, what you're really seeing is motion frozen for an instant, a still image of countless ongoing journeys around a silent golden world. When you move beyond Saturn, the light of the sun begins to lose its sharpness. The distances stretch so wide that sunlight takes more than 2.5 hours to reach the next planet. It arrives weakened, diffused, almost colourless. The shadows here are long and cold, and the boundaries between day and night blur into twilight. In that dim region drifts Uranus, pale, distant, and peculiar. Of all the planets, it is the one that seems to have quietly refused to follow the usual pattern. Where others spin upright or at gentle tilts, Uranus lies on its side. Its equator points almost directly at the sun, and its poles take turns facing the light. Every half orbit it rolls, slowly exposing one hemisphere and then the other to decades of sunlight before darkness returns. Its rotation looks less like a spin and more like a slow tumble. Because of that tilt, about 98 degrees, Uranus experiences seasons like nowhere else. For nearly a quarter of its long orbit, one pole faces the sun continuously, basking in a faint but endless day, while the other endures the same duration of night. Then, as it moves along its 84-year journey around the sun, the balance shifts. The poles trade places. For half a human lifetime, a single region remains in shadow, and then, slowly, light returns. It's a planet defined by extremes, though they unfold so gradually that from one moment to the next, nothing seems to change. Discovered in 1781 by William Herschel, Uranus was the first planet found with a telescope, and the first that expanded humanity's known boundaries of the solar system. It marked the beginning of modern astronomy, the realization that there were more worlds beyond Saturn, unseen by ancient eyes. At first, Herschel thought he had found a comet, but its steady motion proved otherwise. When he realized it was a planet, the map of the solar system grew larger overnight. Later, other astronomers traced its orbit and noticed slight irregularities, hints of another massive body tugging at it, a clue that would lead, decades later, to the discovery of Neptune. Uranus itself is an ice giant, smaller than Jupiter and Saturn, but still immense by any measure. 4 times Earth's diameter, 14 times its mass. Its atmosphere is made mostly of hydrogen, helium and methane. The methane is what gives it its soft blue-green colour, absorbing red light and reflecting blue. Its clouds are faint, often invisible to ordinary telescopes, but spacecraft and advanced imaging have revealed faint streaks and storms, patterns of motion in the calm. There are winds there, hundreds of kilometres per hour, and beneath them, layers of ice and fluid so deep and dense that they behave like oceans of exotic chemistry. When the Voyager 2 spacecraft passed Uranus in 1986, it was the only time humanity has ever seen the planet up close. Even then, the encounter was brief, just a few hours during a long silent flyby. The images it sent back surprised scientists with their subtlety. Unlike the stormy face of Jupiter or the grand rings of Saturn, Uranus appeared calm, almost featureless, a pale turquoise disk hanging in black space. But as data continued to come in, that calm turned out to be deceptive. Beneath the visible layer, Uranus's atmosphere is complex. It rotates in different speeds at different latitudes. It has a magnetic field unlike any other, tilted far from its rotation axis and offset from its centre. That field likely originates in a shell of conductive fluids deep inside, made of water, ammonia and methane compressed into strange forms of matter. Around that tilted, rolling planet orbits a collection of moons that share its quiet eccentricity. As of now, astronomers have identified 27 of them, each one named not after ancient gods, but after characters from the works of Shakespeare and Alexander Pope. Titania, Oberon, Ariel, Umbriel, Miranda, names that sound like a play whispered through the dark. This naming tradition gives Uranus's system a literary softness, a sense of human imagination wrapped around cold reality. These moons are smaller than the great satellites of Jupiter and Saturn, but each has its own terrain, its own story written in ice and shadow. Titania, the largest, is about half the size of our moon. Its surface is marked by valleys and fault lines, evidence that it has stretched and cracked over time. It may have once had, or may still have, a subsurface ocean, though frozen now hidden under its crust. Oberon, its companion, is older and darker, covered in impact scars that have accumulated for billions of years. Ariel is brighter, with long canyons and smooth plains, suggesting that it was once geologically active, that ice may have melted and refrozen in cycles long past. Umbriel, in contrast, is darker and quieter, absorbing most of the faint sunlight that reaches it. It reflects little, making it one of the dimmest major moons in the solar system. Together, these moons create a kind of gradient from brightness to shadow, from motion to stillness. Then there is Miranda, the strangest of them all. It's small, only about 500 kilometers across, but its surface looks like it's been torn apart and stitched back together. Enormous cliffs rise tens of kilometers high, dwarfing any mountain on Earth. Vast canyons cut across its face, separating regions that seem mismatched, like fragments from different worlds combined into one. Scientists think Miranda may have been shattered by impacts and then reassembled by its own gravity. The result is a world that looks both broken and whole, frozen in the act of reforming itself. It's one of those places where you can see the history of the solar system written in literal fractures. All these moons orbit in the planet's equatorial plane, which because of Uranus's tilt lies almost perpendicular to the rest of the solar system. That means they circle around Uranus's poles rather than above its equator as most moons do. From a distance, it would look as if the entire system is rolling on its side, the planet and its moons turning like a wheel through space. The geometry is disorienting. but it's also a visual reminder that normal is just a matter of perspective. Uranus doesn't break the rules of physics, it simply found a different balance. Astronomers believe that Uranus's extreme tilt was caused by a colossal impact long ago, a collision with an Earth-sized body that knocked it over. That impact might also explain why Uranus, unlike other giant planets, emits very little internal heat. Most planets radiate more energy than they receive from the Sun, releasing leftover heat from their formation. Uranus, however, is almost thermally quiet, as if that impact released its internal energy long ago, leaving it in a long, frozen calm. The result is a planet that rotates in silence, carrying the mark of a trauma so ancient that only its motion remembers it. The rings of Uranus are another subtle surprise. They are faint and narrow, discovered by accident in 1977 when the planet passed in front of a star and briefly blocked its light in regular intervals. That pattern revealed a system of dark, thin rings, not the broad, reflective bands of Saturn, but narrow ribbons made of dark material, possibly carbon-coated ice. They lie close to the planet and share its tilted orientation, circling it in planes nearly perpendicular to the solar system's main plane. From certain angles they almost disappear, vanishing into the glare of the planet. Only when light strikes them just right do they appear as delicate outlines, framing the pale blue globe like fine etching. Beyond those rings, the moons continue their silent orbits. Some are small, only tens of kilometers across. Others may still be waiting to be discovered, hidden in the shadows of Uranus's faint light. Spacecraft and telescopes have only begun to reveal their details. Future missions may one day return to explore them more closely, perhaps to orbit Uranus for the first time, to map its moons and measure its mysterious magnetic field. For now, what we know is fragmentary, enough to suggest complexity but not enough to see the full picture. In that way, Uranus remains the most quietly unexplored of the giants, yet even in its remoteness, there's something deeply human about it. Its sideways tilt, its faint rings, its quietly tumbling moons, all seem to suggest a kind of persistence despite difference. It moves through space according to the same laws as every other planet, but it looks different doing it. It rolls instead of spins, it hides its storms beneath a pale mask, it names its companions after dreamers and spirits. If Saturn is a symphony of light and structure, Uranus is a sonata of understatement. Steady, subtle, reflective. If you could stand on one of its larger moons, say Titania or Ariel, the view would be strange and beautiful. The planet would hang in the sky not upright, but sideways, its faint rings glimmering like thin threads across the horizon. The sunlight would be weak, filtered through distance, casting long, dim shadows. A day there would last only a few hours, but the seasons would last decades. For an entire generation, one hemisphere would live in daylight, the other in night. The stars would barely move. Time would feel slower than anywhere else, stretched by the scale of the orbit and the distance from the sun. In such a place, silence would have weight. The cold would be constant, but not empty, filled with the quiet hum of motion, the slow pull of gravity keeping everything in its measured paths. The moons of Uranus don't boast grand features or vibrant colours. They whisper their existence through subtler signs, a crack in the ice, a faint albedo shift, a gravitational nudge that slightly alters the planet's magnetic field. To observe them is to practice patience, to notice the small changes that reveal great forces. The sideways nature of Uranus affects not just how it moves, but how its system interacts. Its magnetosphere, offset and tilted, rotates in complex ways. Its field lines sweep through space like an invisible net, sometimes opening and closing as the planet turns. These dynamics create auroras that flicker near its poles, though they're much fainter than those on Jupiter or Saturn. In ultraviolet light they appear as delicate ovals, brief flashes of energy where charged particles meet atmosphere. Even so far from the Sun, energy still finds ways to express itself. For astronomers, Uranus represents a frontier between the known and the unknown. It's close enough to study, but distant enough that much about it remains a mystery. Its moons, its rings, its interior, all hold questions about how worlds form and evolve. And because Uranus and Neptune are the only ice giants in our solar system, they may also hold clues about the most common kind of planet in the galaxy. When we look at exoplanets orbiting other stars, many of them are Uranus-sized, distant, cold and blue. By understanding this tilted, quiet world, we may also understand hundreds of others scattered across the Milky Way. If you look at Uranus through a telescope from Earth, it doesn't seem dramatic. It's just a small, steady disk of light, faintly blue, with no visible rings or moons. But knowing what it is makes the sight more meaningful. That small dot represents a world rolling through space, carrying with it 27 companions named for the voices of literature, wrapped in a geometry that defies easy order. It's one of the quietest yet most distinct members of the solar system, a planet that seems to move sideways not out of rebellion, but out of history. Past Uranus, the light of the Sun becomes a whisper. It still reaches this far, but it's soft, almost weightless, spreading across billions of kilometers before it touches the next world. Here, heat has almost no meaning. The sunlight that falls on Neptune is about 1,000th as strong as what warms Earth. Shadows are pale and the boundary between night and day fades into a constant blue dusk. This is the outer edge of the planetary family, the place where motion slows, light weakens, and silence becomes nearly perfect. Neptune was the last planet to be discovered, and the first to be found not by chance, but by mathematics. In the mid-1800s, astronomers studying Uranus noticed something strange. Its orbit didn't quite match predictions. It was being tugged by something invisible, something massive and far away. Using those deviations as clues, two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, calculated where that unseen planet should be. When telescopes turned to that spot in 1846, they found Neptune almost exactly where the equation said it would be. It was a moment of pure precision, proof that human understanding could reach into the darkness and find what couldn't yet be seen. Neptune is smaller than Jupiter and Saturn, but heavier than Uranus, a compact world wrapped in deep blue. That colour comes from methane in its atmosphere, which absorbs red light and reflects blue, but its tone is richer and darker than Uranus's, hinting at something deeper and more turbulent below. Neptune is a planet of motion. Despite the faint sunlight, its atmosphere is restless, with winds that are the fastest in the solar system, reaching speeds of more than 2,000 kilometers per hour. Massive storms drift across its surface, appearing and vanishing over weeks. One, known as the Great Dark Spot, was first seen by the Voyager 2 spacecraft in 1989, a vast vortex the size of Earth. When telescopes looked again years later, it was gone, replaced by new ones. On Neptune, even the coldest air can move faster than any storm on Earth. If Jupiter is a planet of gravity and Saturn one of grace, Neptune is a planet of endurance. It receives so little light that its internal heat must be what drives its storms. The planet radiates more energy than it gets from the Sun, a faint reminder that worlds carry warmth from their beginnings. Deep inside Neptune, pressure turns hydrogen, helium and water into strange states. Superheated liquids and ices that behave more like metals. Its magnetic field is tilted like Uranus's and offset from its centre, sweeping through space in uneven waves. Around it, a faint system of rings and arcs drifts quietly, fragile structures made of dust and ice. They're much darker than Saturn's, so faint that they were only discovered when Neptune passed in front of distant stars and briefly blocked their light. Yet Neptune's greatest wonder isn't the planet itself, but its moon, Triton. Almost everything about Triton is unusual. It's large, nearly as big as our moon, but it moves backward. While most moons orbit in the same direction as their planet's rotation, Triton travels the other way, a retrograde orbit that tells a story of capture. Long ago, Triton wasn't a moon at all. It was likely a dwarf planet, part of a population of icy bodies in the Kuiper belt that circles the Sun beyond Neptune. At some point, it wandered too close. Neptune's gravity caught it, pulled it in, and made it part of its system. That capture wasn't gentle. It would have caused massive tidal heating, melting Triton's interior and reshaping its surface. Over time, it settled into its strange backward path. Because of that capture, Triton's orbit is unstable. Slowly it's spiraling inward, losing altitude as it interacts with Neptune's gravity. One day, perhaps in hundreds of millions of years, it will come too close. When that happens, the same tidal forces that tore apart a moon to create Saturn's rings will act here too. Triton will shatter, and Neptune will gain new rings, bright for a time, glowing faintly in reflected sunlight, before they too drift away. Even out here, so far from everything familiar, the cycle continues. Creation, capture, and loss, repeated endlessly. Triton's surface is a mixture of ices, nitrogen, water, and methane frozen solid. But it isn't still. When Voyager 2 flew past it, the spacecraft's cameras caught something astonishing. Geysers. Plumes of nitrogen gas shooting kilometers high from the surface, leaving dark streaks as they fell back down. That discovery made Triton the first active world seen in the outer solar system. Despite the cold, nearly minus 230 degrees Celsius, there is movement, energy, and change. The thin layer of sunlight that reaches it warms the surface just enough to turn solid nitrogen into gas. As that gas escapes, it vents through the crust, creating those geysers. Beneath that surface, there may even be a hidden ocean, kept liquid by the faint heat left from its capture and the decay of radioactive elements. Seen from Neptune, Triton would be brilliant, its icy crust reflecting sunlight, moving slowly across the sky in the opposite direction of the planet's spin. Sometimes it would eclipse the sun, casting long shadows across Neptune's blue clouds. From Triton's surface, the view would be haunting. Neptune would fill a large part of the sky, a turquoise giant glowing in the dim light, surrounded by faint rings and distant stars. You would see the planet's storms drifting far below, watch its shadow move across the rings, and know that everything here, the light, the motion, the silence, is slower than time feels anywhere closer to the sun. Triton's retrograde path isn't just unusual, it changes everything about Neptune's gravitational environment. Because it moves opposite the planet's rotation, its tides pull in reverse, slowing Neptune slightly and altering the orbits of smaller moons around it. Neptune has 13 confirmed moons, most of them small, irregular shapes captured like Triton but without its prominence. They orbit in eccentric paths, reminders of the planet's long history of gravitational encounters. Some may be remnants of earlier moons destroyed when Triton was captured. Others may be fragments of comets that drifted too close. In Neptune's realm, companionship is temporary and often accidental. Objects passing, merging, or disappearing without ceremony. The planet itself has no solid surface. Its atmosphere thickens until it becomes fluid, a deep ocean of hydrogen, helium, and water under crushing pressure. Somewhere below that, perhaps near its core, temperatures reach thousands of degrees. Scientists think that under those conditions, carbon could crystallize into diamonds. It's possible that diamond rain falls deep inside Neptune, sinking slowly toward its core. It's a poetic image, but a physical one too. A reminder that even in extreme environments, matter finds new forms of order. Voyager 2's brief visit gave humanity only a glimpse of Neptune and its moon. The images it returned remain some of the most haunting in planetary science. Neptune glowing in deep blue, a small white cloud casting a shadow across its surface, Triton trailing behind like a pale companion. Since then, no spacecraft has returned. The distance makes it difficult. The cold and faint sunlight limit energy. Yet, with new technology and renewed interest in the outer solar system, there are plans to go back. Missions have been proposed to orbit Neptune, to study its atmosphere and to land or fly close to Triton, searching for signs of internal heat or subsurface water. Even now, the data we have from that single flyby still raises more questions than it answers. The chemistry of Neptune's atmosphere is another mystery. Methane gives it colour, but the deeper layers may contain complex compounds that shape its weather. Its winds are powered not by sunlight, but by internal energy, rising from the planet's interior and driving currents that circle the globe. Despite its calm appearance from afar, Neptune is one of the most active atmospheres in the solar system. The contrast between distance and dynamism makes it an outlier. A world that seems quiet but hides storms stronger than any closer to the Sun. If you could hover above Neptune's clouds, the view would feel almost abstract. The planet has no visible landmarks, no mountains or plains, just continuous motion. Clouds of methane ice drift in bands, vortices spin and dissolve, lightning flashes faintly through the haze, illuminating layers for fractions of a second. It's a landscape without edges, a world defined entirely by movement. In that sense, Neptune is pure fluidity, a place where matter never rests long enough to form structure. Its faint rings, named after astronomers who contributed to its discovery, Adams, Leverrier, Gall, and Lassell, are made of dark material, possibly coated with organic compounds. Within them are arcs, sections that are denser than others, held together by the gravity of small moons. Unlike Saturn's symmetrical bands, Neptune's rings are patchy, irregular, almost shy. They appear and fade depending on how sunlight catches them. They seem to resist permanence, like everything else here. When you imagine Neptune's system as a whole, it feels like a world holding on to its companions through sheer gravity and time. Its moons, its rings, its faint magnetic field, all in slow, silent motion, balanced just enough to endure for now. But that endurance is temporary. Triton's slow inward drift will eventually change it all. The outer moons may be scattered, the rings reshaped. Even Neptune's rotation may alter slightly. These changes will happen over millions of years, so gradual they're invisible to us yet constant. The solar system isn't static. It's always adjusting, redistributing, finding new equilibrium. Neptune reminds us of that. The idea that stability isn't stillness, it's balance through motion. The name Neptune, taken from the Roman god of the sea, feels fitting not just because of the planet's colour, but because of its nature. Everything about it suggests depth, unseen layers, hidden currents, vast and mysterious calm hiding constant motion. It's the sea turned into a planet, a world defined by what it conceals. And in its orbit, Triton becomes both its companion and its reflection, a captured traveller that mirrors Neptune's quiet defiance of the usual order. Together they form one of the most complex relationships in the solar system, a planet and a moon moving in opposition, bound by a gravity that will one day destroy one of them, but in doing so create something new. Even here, at the edge of the known planetary world, companionship persists. The sun is distant, but it still ties Neptune and Triton to everything else. Gravity connects them back to Uranus, to Saturn, to Jupiter, to Earth, to you. That invisible link threads through space, unchanged by distance. It's easy to think of the outer planets as remote and irrelevant, but their presence shapes the solar system's stability. Their gravity protects the inner world, steering comets and debris away, preserving the conditions that make life possible closer to the sun. Even the farthest planets play their part. And beyond Neptune, the pattern continues. There are still smaller worlds circling the Sun, icy remnants that mark the boundary between planets and deep space. Pluto, Eris, Haumea, Makemake, dwarf planets that orbit in the dark, each with their own moons, each with their own quiet systems. Out there, the solar system begins to dissolve into the greater cloud of the Kuiper Belt, where sunlight fades into starlight and the line between orbit and freedom blurs. Neptune is not an ending, it's a threshold. Beyond it lies the vastness that once seemed infinite, the realm of the forgotten and the new. Beyond Neptune, the solar system begins to fade into distance so great that light itself feels slower. The sun is still there, but it's no longer a source of warmth. It's a bright star hanging in an endless black, surrounded by the cold that defines almost everything this far out. Here lies the region once thought to mark the end of our planetary family, a place of mystery and quiet persistence. For much of the 20th century, this outermost world was known as the ninth planet. We called it Pluto, and for generations it represented both the edge of the solar system and the limit of our reach. Discovered in 1930 by Clyde Tombaugh, Pluto was the product of both careful observation and patient luck. Tombaugh had been assigned to search for a hypothetical planet predicted by small irregularities in Neptune's orbit. Using photographic plates taken days apart, he compared them under a microscope, searching for a tiny point of light that moved slightly against the background of stars. After months of work, he found it, a faint, shifting spot. That small moving light became the most distant known planet at the time, an emblem of exploration, a symbol that even at the edges discovery was still possible. For decades, Pluto held a firm place in textbooks. It was small, cold, and faint, but it was ours, a frontier. Generations of students memorized its name as the last stop on the planetary list. Then, near the end of the 20th century, new discoveries began to shift that view. Astronomers found other icy bodies beyond Neptune, some nearly as large, orbiting in elongated paths far from the Sun. The region that contained them came to be known as the Kuiper Belt, a vast flattened ring of frozen debris left over from the solar system's formation. When Eris, a world slightly smaller than Pluto but with a similar orbit, was discovered in 2005, it forced a question: what exactly is a planet? The answer, decided in 2006 by the International Astronomical Union, changed everything. Pluto was reclassified as a dwarf planet, along with Eris and several others. It wasn't a demotion in a personal sense, because Pluto hadn't changed, but our definition had. To be a planet, an object must orbit the Sun, be large enough for gravity to make it round, and clear its orbit of other debris. Pluto met the first two conditions, but not the third. It shared its orbital space with other bodies in the Kuiper Belt, and so it was moved into a new category, smaller but still significant. For many, the change felt emotional, as if something familiar had been taken away. But scientifically, it was a reflection of growth. We had learned that Pluto wasn't alone, and that knowledge reshaped our understanding of what the outer solar system really is. Pluto's orbit is unlike the others. It's tilted and stretched, crossing inside Neptune's path at one point, then swinging far beyond it. A full revolution takes 248 Earth years. For a brief portion of that time, about 20 years, Pluto is actually closer to the Sun than Neptune. Its path is stable, locked in a resonance with Neptune's gravity, so they never collide. But the crossing is another reminder that the solar system's structure is not as neat as diagrams suggest. Out here, orbits weave and overlap, creating a slow choreography shaped by billions of years of motion. When the New Horizons spacecraft reached Pluto in 2015, it was the first and only visitor to this distant world. After travelling for nearly a decade, covering more than 4 billion kilometres, it flew past at 60,000 kilometres per hour, capturing images and data in the few hours it could before continuing into the void. The pictures it sent back were astonishing. Pluto, once thought to be a dull, frozen rock, turned out to be a dynamic, complex world. Its surface was marked by mountains of water ice, plains of frozen nitrogen, and glaciers that still move. There were cliffs, valleys, and even haze in its thin atmosphere. One region, a vast heart-shaped plain called Sputnik Planitia, became the planet's most recognizable feature. A smooth expanse of nitrogen ice surrounded by rugged highlands. That image, a small heart on a distant world, changed how people thought of Pluto forever. Pluto's atmosphere is delicate, made mostly of nitrogen with traces of methane and carbon monoxide. When it's closest to the Sun, some of its surface ice sublimates, turning directly from solid to gas, creating a thin, blue-tinged atmosphere that can rise hundreds of kilometers above the surface. As it moves farther away, that atmosphere begins to freeze again, falling as snow back to the ground. Its seasons are long, slow, and severe. Each one lasts for decades. The sunlight that reaches Pluto is so weak that it feels more like a pale memory of warmth than heat itself. Yet, even here, the planet changes. The ice moves, the air thins and thickens, and shadows lengthen and shift across mountains and plains. Pluto's relationship with its largest moon, Charon, is one of the most extraordinary in the solar system. Charon is so large, about half of Pluto's diameter, that the two bodies orbit a point in space outside of Pluto itself. It's a true binary system, a pair of worlds locked in balance. They always show the same face to each other, their rotation synchronized. To someone standing on Pluto, Charon would never rise or set. It would hang in the same spot in the sky, its pale surface glowing faintly in the dim sunlight. From Charon, Pluto would appear equally fixed, a reddish world with bright patches of frost. They orbit each other every 6 Earth days, turning slowly together in silence. Charon's surface tells its own story. It's covered in water ice and marked by vast canyons, some deeper than the Grand Canyon, evidence that its crust once expanded as internal water froze and pushed outward. Near its pole lies a dark region unofficially called Mordor Macula, likely made of material pulled from Pluto's escaping atmosphere. The two bodies exchange matter, a slow, invisible transfer of molecules that links their surfaces. Their relationship isn't static, it's dynamic, shaped by gravity and time. Together they represent a kind of equilibrium that's rare among worlds. Pluto also has smaller moons, Styx, Nix, Kerberos and Hydra, each irregular, each spinning chaotically as they orbit the binary pair. Their paths are influenced by both Pluto and Charon, creating a gravitational complexity that keeps them constantly adjusting. Some of them rotate so irregularly that they have no consistent day or night cycle. They tumble as they move, their orientations changing unpredictably. From afar, the system looks like a miniature solar system in disarray, with each moon following its own rhythm, yet all held by the same centre of gravity. The New Horizons mission showed that Pluto's geology is surprisingly active for a world so small and cold. Its mountains, some higher than Everest, are made not of rock but of water ice, strong enough to act like stone at such low temperatures. The smooth plains of Sputnik Planitia show signs of convection, slow movement of ice driven by internal heat. Beneath the surface there may even be a subsurface ocean of liquid water, kept from freezing solid by residual heat and pressure. If that ocean exists, it means that even here, billions of kilometers from the Sun, there could be environments where chemistry continues, where complex molecules form, where the potential for life, however minimal, still flickers. Pluto's light is faint, but it has an atmosphere that scatters sunlight in shades of blue, similar to Earth's twilight. New Horizons captured an image of the planet backlit by the Sun, showing a thin halo of light around it, the atmosphere glowing softly against the blackness. That photograph became one of the most iconic images of the mission. a symbol of how even the most distant worlds can surprise us with their beauty. The surface colours of Pluto are varied: reddish browns, pale yellows, icy whites, the result of chemical reactions driven by sunlight acting on methane and nitrogen. These reactions create complex organic molecules called tholins, which give Pluto its characteristic hues. Over time, radiation from space alters those compounds, deepening the colour, layering history into the crust. Each tone tells a story of exposure, chemistry, and time. The planet's brightness changes slightly as it rotates, showing different regions with each turn. For many years, Pluto's distance made it seem unreachable, but that remoteness is part of its meaning. It represents not just the outer boundary of our planetary system, but the persistence of curiosity. The same impulse that sent telescopes searching for Neptune's unseen influence led to Pluto's discovery, and the same drive that reclassified it also sent new horizons to visit it. Each step shows that knowledge isn't a destination, it's a motion outward, one discovery leading to the next. Pluto's story is less about what category it belongs to, and more about how it connects to everything around it. Beyond Pluto, the Kuiper Belt continues. It's filled with thousands of small icy bodies, remnants from the solar system's creation. These objects, sometimes called trans-Neptunian objects, follow wide, eccentric orbits that stretch for billions of kilometers. Some of them, like Eris, Haumea, and Makemake, are large enough to be spherical, dwarf planets in their own right. Others are irregular, fragments of collisions or captured debris. Together they form a transitional zone between the orderly world of the planets and the scattered edge that leads into interstellar space. The Kuiper Belt is not empty, it's full of motion, faint, slow, distant, but constant. As New Horizons continued its journey, it passed another Kuiper Belt object, Arakoth, in 2019. That small, contact binary world, two lobes fused together, gave scientists their first close look at the building blocks of planets. Arakoth is ancient, nearly unchanged since the solar system's formation. Its shape, colour, and composition reveal how small icy bodies merged billions of years ago to form larger worlds. Seeing it was like looking back in time to the solar system's earliest days. Pluto and its neighbours are what remains of that era. Frozen archives of creation, drifting quietly beyond the sun's warmth. To call this region forgotten is only half true. For much of history it was simply unseen. It wasn't that we ignored it, it's that we didn't know it existed. Now, with new telescopes scanning the deep sky, we can detect faint points of light moving slowly through the dark, each one a world in its own right. The frontier isn't gone, it's just farther away. What we used to call the edge has become a gateway. If you could stand on Pluto or Charon and look up, the sky would be black, even in daytime. The sun would appear no larger than a bright star, its light a pale glow that casts long shadows across frozen plains. The stars would be sharp and unwavering. You could see other members of the Kuiper Belt, tiny specks of motion across the background. Occasionally, you might see Charon or one of the smaller moons drifting slowly across the horizon, their light reflecting softly from the sun, so distant that it feels symbolic more than physical. The silence there would be complete, but not empty. It would carry the presence of everything that came before: the inner worlds, the gas giants, the paths of comets, the faint traces of light still moving outward. In that stillness, Pluto stands as a reminder that even at the furthest edge, there are stories unfolding, cycles continuing, and motion persisting. It's a place where orbits become almost philosophical, not just circles of gravity, but expressions of connection. Beyond Pluto, the solar system doesn't end abruptly. It thins gradually into the scattered disk, where icy bodies follow elongated orbits that can take thousands of years to complete. Some are flung outward by Neptune's gravity. Others drift inward occasionally, becoming comets that visit the inner system before returning to the dark. Eventually, those orbits reach the outermost region, the Oort cloud, a vast sphere of frozen material surrounding the solar system like a shell. From there, the Sun is only another star among many, and yet every particle in that cloud still belongs to it, still moves because of it, still carries its gravitational mark. The forgotten frontier isn't empty space, its continuity stretched thin. It's the place where the solar system fades into interstellar space, where the boundary between what belongs to the Sun and what doesn't becomes uncertain. Pluto and its companions drift there not as endings, but as reminders that even the most distant parts of the universe remain connected by invisible lines of motion. The frontier, as it turns out, was never meant to be a wall. It's a horizon, one that keeps moving as we do. Beyond Pluto, the Sun still reaches, but its light no longer feels like something that shines. It's more like a memory, a diffuse glow stretched thin across a distance so wide that even light takes hours to cross it. The solar system doesn't stop here. It doesn't end at a boundary or fade into sudden emptiness. Instead, it continues gradually, like the last ripples of a wave that began billions of years ago. In this outer region, planets give way to remnants, fragments of ice and rock left over from creation. These are the dwarf planets and trans-Neptunian objects, drifting through the dark on paths so long that a single orbit can outlast the rise and fall of civilizations. Astronomers once thought that Pluto marked the frontier, the farthest outpost of our star's influence. But with better telescopes and longer surveys, they began to see faint points of light moving slowly against the background of stars, not random debris, but worlds. The first to stand out among them was Eris, discovered in 2005. It's nearly the same size as Pluto, though slightly denser, with a reflective surface of frozen nitrogen and methane. For a time, its discovery was what forced the question of what makes a planet a planet. But beyond its historical role, Eris is a place in its own right, a small, bright world orbiting the Sun 3 times farther out than Pluto. Its path is long and tilted, taking it hundreds of years to complete a single loop. Around it orbits a small moon named Dysnomia, discovered soon after. Together they move through the cold, untouched space beyond Neptune, silent and precise. Eris is bright enough that sunlight still reaches it, but not in any familiar way. From its surface, the Sun would look like a single dazzling star, perhaps 100 times brighter than the full moon appears from Earth. Daylight there would resemble twilight, pale, bluish, indirect. Shadows would stretch endlessly across frozen terrain. The temperature is so low that air cannot exist. Any trace of gas freezes instantly. The surface is hard, smooth, and quiet, coated with ice that reflects light like glass. It's a world of stillness, shaped more by gravity and time than by weather or erosion. The only change is slow, a gradual darkening of the ice as cosmic radiation alters its chemistry, a faint reddening that marks the passage of eons. Not far from Eris, in astronomical terms, lies Haumea. It's one of the strangest known dwarf planets, elongated, spinning rapidly, shaped more like an egg than a sphere. It rotates once every 4 hours, the fastest of any large body in the solar system. That speed stretches it, pulling its equator outward so that it looks like it's been caught mid-motion. Haumea's surface is bright, covered in crystalline water ice, which suggests that it's relatively young or frequently renewed. Around it orbit 2 small moons, Hi'iaka and Namaka, named from Hawaiian mythology, in honor of the observatories that first studied it. Haumea's fast spin and family of moons hint at a violent past, perhaps a collision that shattered part of its outer layer, creating the moons and sending fragments into their own orbits. It's a reminder that even in the cold quiet of the outer solar system, motion and impact still shape everything. Then there's Make, another dwarf planet, slightly smaller than Pluto but with a similar composition. Its name comes from the Rapa Nui creator deity of Easter Island, a link between one of the most remote places on Earth and one of the most remote in space. Makemake reflects sunlight from a surface of frozen methane, giving it a reddish hue. It also has a tiny moon, discovered in 2016, that orbits close and faintly, like a hidden companion. These distant worlds, Pluto, Eris, Haumea, Makemake, together form the known core of the Kuiper Belt's large members. But beyond them lies something even more tenuous, the scattered disk, where orbits grow elongated and tilted, reaching thousands of astronomical units into space. The scattered disk is like a transitional zone between the organized system of planets and the unbound realm beyond. Its objects move in stretched ellipses, sometimes looping back near Neptune, sometimes drifting far into darkness before returning centuries later. One of these objects, Sedna, has an orbit so long and stretched that it spends most of its time more than 10 billion kilometers from the Sun. A single Sedna year lasts over 10,000 Earth years. Its path never comes close to Neptune, suggesting that something else may have disturbed it long ago. Perhaps a passing star or a massive, still undiscovered planet lurking in the far reaches of the solar system. Sedna's discovery in 2003 reignited a quiet mystery. Its orbit is too large to have been shaped only by the known planets. It doesn't fit neatly within the Kuiper Belt or the scattered disk. Instead, it seems to trace the inner edge of a much larger structure, the Oort cloud, a vast sphere of icy bodies that surrounds the solar system at distances so great that they blur the boundary between our star's influence and interstellar space. Sedna may be a messenger from that frontier, an object that moves between two gravitational realms, neither fully bound nor fully free. If you could see Sedna from up close, it would look like a small reddish world, perhaps 1,000 kilometers wide, its colour the result of tholins, complex organic compounds formed by cosmic radiation acting on simple ices. Its surface would be cold enough that even nitrogen and methane remain frozen solid. The sunlight would be so weak that shadows would barely exist. Time there would feel endless. The stars would look unchanged for centuries. Even the sun's light would arrive more than 10 hours after leaving its source. In such an environment, the concept of day becomes almost meaningless. It's a world where change happens in glacial increments, where every motion is a trace of something that began billions of years ago. The Oort cloud, if we could see it, would be a vast invisible shell surrounding the solar system, extending perhaps halfway to the nearest stars. It's made of trillions of icy objects, comets, fragments, and frozen debris, all held loosely by the sun's gravity. Occasionally one of these bodies is nudged inward by the pull of a passing star or the slow influence of the Milky Way's tides. When that happens, it begins a journey that can take millions of years, falling toward the sun. As it nears the inner solar system, it warms and its ices vaporize, forming the glowing tails we see from Earth. Every comet is a visitor from that distant frontier, a brief emissary from the edge. They remind us that the solar system isn't closed or static, it breathes, exchanging matter with the darkness beyond. What lies even farther out is something we can only infer. At those distances, direct observation becomes almost impossible. The objects are too faint, their motion too slow, but gravity leaves clues. Subtle patterns in the orbits of distant bodies suggest the presence of something massive, perhaps a ninth planet, a world many times larger than Earth, orbiting far beyond Pluto. No telescope has found it yet, but the search continues. Whether it exists or not, the possibility itself speaks to the vastness still uncharted. The solar system, even after centuries of study, remains incomplete. In the outer darkness, light behaves differently. It doesn't illuminate as much as it grazes, sliding across surfaces rather than brightening them. Worlds here are half seen, their details revealed only by reflected glints. Yet those reflections are enough to map their orbits, measure their sizes, and understand their nature. They are time capsules, preserved remnants of the early solar system, made of the same materials that built Earth and the other planets. By studying them, astronomers can reconstruct how everything began, how dust clumped into rock, how rock gathered into worlds, and how those worlds migrated to their current positions. The Kuiper Belt and beyond are not endings, they are archives. When New Horizons completed its flyby of Pluto, it didn't stop. It continued onward into the Kuiper Belt, visiting Arakoth, a contact binary shaped like two spheres gently fused together. That small object, only about 30 kilometers long, is one of the most primitive ever observed. Its smooth, undisturbed surface suggests it formed slowly, without violent collisions, in the calm outer reaches of the young solar system. Seeing it up close was like peering into a memory older than Earth itself. Arakoth's shape, two worlds joined but distinct, is an image of how planets begin, through connection, not impact. Even at the edge, the same forces that built everything are still visible. If you were standing on one of these distant worlds, the universe would look vast and unmoving. The sun would be a small, intense point. Its light would travel across frozen plains, reflecting off ice crystals suspended in nothing. The stars would seem sharper than anywhere else, because there would be no air, no motion, no interference. The silence would not just be absence, it would be structure, the soundless weight of distance itself. Every direction would look the same, every point in space a reflection of how small our solar home really is. And yet, despite that isolation, there's still a trace of connection. Every one of these objects, Eris, Haumea, Makemake, Sedna, and countless others, still orbits the same centre. They are still bound to the sun, their paths curved gently by its gravity. That bond, though faint, defines them. It's what separates them from interstellar wanderers. They are still part of our system, still moving in the long rhythm that began when the sun ignited. Even at the furthest edge, the solar system hasn't let go of its own. This region, the Kuiper Belt, the scattered disk, the Oort cloud, is not empty but transitional. It's where the solar system begins to merge with the galaxy itself. Here, the influence of other stars becomes real. Their gravity tugs subtly on the outermost objects, slowly reshaping their orbits over millions of years. The sun's reach ends not with a line, but with a fade, like a shadow blending into another. Beyond this, there's no clear border, only the slow handover of gravity from one star to the collective pull of all the others. The space between stars is not a void, it's a continuum. Some of the comets that fall toward the inner solar system may never return. The energy from their encounters can fling them into open trajectories, sending them outward forever. Those that do return trace long, repeating arcs, bringing with them stories from the coldest parts of space. Each comet, each icy fragment, is a reminder that what we think of as the solar system is more than just planets. It's a living network of motion extending far beyond what we can see. If you follow one of those comets outward far enough, the sun will eventually shrink to a bright pinprick, indistinguishable from the surrounding stars. The warmth will vanish completely. Space will become what it mostly is, dark, still, and indifferent. But even there, a faint gravitational tether remains. The sun's influence extends for trillions of kilometers, defining a bubble of space called the heliosphere. Inside it, solar wind, a stream of charged particles, pushes outward, meeting the thin gases of interstellar space. Where those two forces balance lies the true edge of the solar system, a boundary not of matter, but of motion and influence. The Voyager spacecraft, launched in 1977, have now crossed that boundary. They are still travelling outward, carrying messages from Earth in the form of golden records, human sounds, images, and greetings. They continue to send back faint signals, whispering data across a distance measured in light days. Each one is a small moving world of its own, a human-made moon of the sun, drifting into the same darkness that the outer planets and dwarf worlds inhabit naturally. Their presence there makes the edge feel less abstract. The frontier, once unreachable, now contains something of us. In the vast quiet beyond Neptune and Pluto, there are still patterns, still orbits, still relationships. Even when the Sun is only a star among many, its influence can still be traced. That continuity, the persistence of motion and connection, defines what it means for something to belong. The solar system doesn't end at the edge of visibility. It continues as long as gravity holds, as long as there's anything left to circle something else. And so, when we look outward, what we see isn't emptiness, but a widening of context. The dwarf planets and the distant comets, the faint rings around unknown worlds, the slow orbits of objects we've barely begun to count, all of them are part of the same structure, the same ongoing story. The frontier isn't forgotten, and it isn't final. It's simply the next orbit waiting to be understood. Even after centuries of looking upward, the solar system still holds more companions than we've counted. Every year, telescopes reveal new points of light orbiting distant worlds, faint, slow-moving dots that turn out to be moons. We've catalogued hundreds of them now, from the great spheres of Jupiter and Saturn to the small, irregular fragments circling the outermost planets. And yet, the count keeps changing. There are moons we've seen and forgotten, moons we've confirmed and renamed, and countless others that remain invisible for now. Too small, too dim, or too far away to appear even in the sharpest images. Somewhere in the shadows of the gas giants, in the glare of their rings, or drifting quietly around dwarf planets, more moons are waiting to be found. The search for moons is as much about patience as it is about discovery. Many of the smallest ones orbit so close to their planets that they vanish in brightness. Others move so far away that they disappear into darkness. Some are fragments, only a kilometre wide, tumbling in our irregular paths. They reflect just enough sunlight to be seen for a few hours each year, and then they fade again. Finding them requires repetition, returning to the same sky over and over, comparing faint changes, watching a pixel shift slightly against the background of stars. In recent years, new telescopes and advanced imaging techniques have allowed astronomers to uncover dozens of previously unknown moons around Jupiter and Saturn. These discoveries often happen quietly, through data analysis rather than observation by eye. Images captured over weeks are layered and compared, and in those alignments, a small pattern emerges, an object that moves when the stars do not. Sometimes the same process is applied to older photographs, revealing moons that were hiding in plain sight. Each one adds to the growing realization that the solar system's companionship is more crowded than we ever imagined. Around Jupiter, the known count has risen past 90. Most of these moons are tiny, fragments of once larger bodies that broke apart under tidal stress or collision. They orbit far from the planet in clusters that share similar inclinations and distances, suggesting common origins. Some move in the same direction as Jupiter's rotation, others, captured from elsewhere, orbit backward. They're irregular, their paths stretched and tilted, forming a cloud of slow-moving stones bound by gravity alone. It's possible that dozens more still exist, unseen, faint and distant, too small for even our most powerful instruments to resolve clearly. They may orbit beyond the outermost known ones, tracing invisible paths through the planet's vast sphere of influence. Saturn's system, though better studied, is likely just as incomplete. The Cassini spacecraft revealed dozens of small moonlets embedded within its rings, each one sculpting the icy bands with its gravity. Some of these are temporary, pieces of ice that may merge, split, or disintegrate over time. Others orbit in gaps, invisible except when they disturb the ring structure around them. As the rings evolve, new moons could form from their material, while old ones may fall apart. Saturn's count is fluid, changing as the system reshapes itself, Even now, computer models suggest that there may be hundreds of objects large enough to qualify as moons, hiding within or near the rings, too faint to distinguish from the background of ice and dust. The outer planets likely harbour even more unseen companions. Uranus, with its sideways rotation and dim rings, has a collection of known moons, but its system remains only partially mapped. The Voyager 2 flyby in 1986 discovered 10 small moons that had never been seen before, simply because of how close they orbit and how faint they appear. Since then, ground-based telescopes and the Hubble Space Telescope have added more, but simulations suggest there could be dozens still waiting, perhaps hidden in the planet's faint ring shadows. Some might be so dark that they absorb almost all the light that reaches them. Others might be too close to the glare of Uranus itself, visible only during brief moments when their reflected light separates from the planet's brightness. Neptune's system too is incomplete. Beyond its largest moon, Triton, lies a collection of small, irregular moons discovered only in the past few decades. Some orbit in distant, tilted paths, hinting at a complex history of capture and disruption. In 2013, astronomers discovered a 14th moon using images from the Hubble Space Telescope, a tiny object only about 20 kilometers wide, orbiting between two larger moons. It had gone unnoticed for years, hidden in archival data. If such a small moon can remain undetected so close to a planet already studied by spacecraft, it's certain that others exist beyond our current limits. Neptune's gravity extends far into the dark, and within that reach, fragments from old collisions or captured debris from the Kuiper Belt could still circle unnoticed. Even the dwarf planets likely have their own unseen companions. Pluto has 5 known moons, but smaller objects may still orbit farther out or closer in, too faint to detect. Eris, Haumea, Makemake, and others each have at least one known moon, but those systems could be more complex than we realise. The dim light, great distance, and slow orbits make observation difficult. Some of these moons might even share their parent world's strange shapes and rapid rotations, remnants of collisions from the solar system's early years. In that era, impacts were common, and debris from those events often stayed nearby, coalescing into smaller satellites over time. Many of the outer moons we know today, and many we have yet to find, were born from that process. Finding new moons isn't just about counting, it's about understanding how systems form and evolve. Every moon, even the smallest, carries information about its planet's history. Its orbit reveals how gravity sculpted the system. Its composition hints at whether it formed with the planet or was captured later. Its motion tells us how time and distance shape the balance of forces. By studying the faintest and most distant moons, scientists can reconstruct events that happened billions of years ago, when the solar system was still forming. Sometimes new moons appear not through discovery, but through reinterpretation. Data from spacecraft and telescopes can be reanalyzed years later with new methods, uncovering details that were missed. Anomalies in a planet's gravitational field, faint streaks in old images, or small fluctuations in reflected light can all reveal hidden companions. The process is slow, but the results remind us how much of the solar system's story remains unread. Some astronomers believe that we may never know the exact number of moons in our solar system, because the definition itself is flexible. What counts as a moon? Does it need to be spherical, or can it be an irregular rock a kilometre wide? Should we count temporary satellites, small asteroids that drift near Earth or Mars for a few months before leaving their orbits? In the language of motion, even those brief visitors qualify. At any given moment, our planet might have 1 or 2 of these temporary companions, captured by gravity for a while, then released again. They are moons in the most literal, fleeting sense. Around Earth, small asteroids occasionally enter short-lived orbits, circling for a few revolutions before escaping back into space. These are our planet's unofficial moons, unnamed, unnoticed, and constantly replaced. Around Jupiter and Saturn, the situation is similar on a larger scale. Their immense gravity fields can temporarily capture passing comets or asteroids, keeping them for years or even centuries before letting them go. The boundary between permanent and temporary moons is blurred, and that makes the count both richer and more uncertain. There's also the possibility that some moons exist in places we haven't yet thought to look. Around the largest asteroids, for instance, small satellites have been found by chance. The asteroid Ida was discovered to have a tiny companion named Dactyl when the Galileo spacecraft flew past it in 1993. Since then, similar pairs have been found among many other asteroids. Even comets, once thought to travel alone, can split and form temporary companions of their own. These relationships are fragile, fleeting, but common. The solar system seems to prefer companionship, even in miniature. When astronomers talk about the moons we haven't found yet, they aren't just referring to small objects hidden in darkness. They're also referring to what those moons represent: the uncounted, the unnoticed, the possibilities that remain. The discovery of each new satellite adds a piece to the pattern, revealing how widespread the phenomenon of orbit truly is. Every large body attracts smaller ones. Every centre finds something to circle it. It's not an exception, but a rule, repeated endlessly across the universe. Technological advances will continue to reveal more. The upcoming generation of telescopes, on Earth and in space, will be able to detect objects thousands of times fainter than before. The Vera C. Rubin Observatory, for example, will scan the entire sky repeatedly, catching movement in places once too faint to study. As it does, new moons will appear, small dots shifting across frames, the first signs of objects that have been circling their planets unnoticed for billions of years. These discoveries will likely redefine what we think we know, showing that even the giants we thought familiar still hold surprises. There's also the possibility of moons around exoplanets, worlds orbiting other stars. So far we've detected thousands of exoplanets, but only tentative hints of their moons. The distances are enormous and the effects subtle. Yet, with every refinement in observation, the chance of detecting a true exomoon increases. When that happens, when we confirm the first moon around a planet beyond our solar system, it will mark a quiet milestone. It will show that the pattern of companionship we see here isn't unique to us, but universal. The moons we haven't found yet, whether in our system or another, remind us that discovery is ongoing. The universe isn't waiting to be completed. It's revealing itself gradually, one orbit at a time. Every new detection changes our sense of scale, expanding the definition of what home includes. The unseen moons aren't just physical objects, they're symbols of what remains possible to know. If you imagine all these unseen companions together, the small tumbling stones near Jupiter, the faint ring moons of Saturn, the hidden fragments around Uranus and Neptune, the distant partners of dwarf planets, and even the exomoons that circle unseen worlds, you begin to sense a pattern that extends far beyond numbers. It's the same rhythm repeated endlessly, something large holding something smaller, something massive shaping something fragile. Gravity is the language of connection, and moons are its most enduring expression. Perhaps the most humbling part of the search isn't how many we've found, but how many remain. Even after centuries of looking, we're still only seeing the brightest points in a vast field of darkness. But the darkness isn't empty. It's full of motion waiting to be resolved into light. Somewhere, in the glare of a giant planet or the faintness of a dwarf world, another moon turns quietly, unseen but existing all the same. And as we move further into understanding these hidden companions, the question shifts. It's no longer just how many moons we have, but what they mean, what they tell us about connection, formation, and time. Every new moon discovered adds another note to the same melody, the one that began billions of years ago when dust and gas first gathered under gravity's pull. The pattern hasn't stopped. It continues beyond sight, beyond count, beyond certainty. Farther still, Beyond the known planets and their unseen companions, the question of definition itself becomes more complex. What makes a moon distinct from a fragment from a ring from a cloud of debris? The more we learn, the less clear those borders become, and perhaps that's the quiet truth of it, that the solar system isn't built of clear separations but of gradients, transitions and continuities. Every boundary blurs into another, every orbit connects to the next. Even now, as technology expands our vision, there will always be more hidden than revealed. The cosmos ensures that mystery remains. The moons we haven't found yet are as much a part of that mystery as the ones we have. Their invisibility is part of the balance, a reminder that knowledge is never complete, that discovery is a horizon always just ahead. The farther we travel through the solar system, the less certain the word moon becomes. At first, it seems like a simple definition, a natural satellite that orbits a planet. But as our understanding expands, that simplicity starts to blur. Some moons are large enough to hold atmospheres, to host oceans, to resemble planets themselves. Others are so small that they barely hold together, tumbling through space like fragments. Some were born from their planet's material. Others are captured wanderers. A few don't even orbit planets at all, at least not permanently. And somewhere among them, we realise that the question isn't only how many moons there are, but what makes a moon in the first place. For Earth, the answer feels easy. Our moon is singular and stable. It orbits us cleanly, affects our tides, and shines brightly in the night sky. It's large enough to have shaped our evolution, our calendars, our myths. It has a clear identity, a world bound to ours by gravity and history. But the rest of the solar system doesn't follow that pattern. Around the giants, moons come in swarms. Some share orbits, some move backward. Some are captured asteroids that may not remain forever. The more we study them, the harder it becomes to find a single line that separates moon from object. At its most basic, the definition begins with motion. A moon is something that orbits a planet, or more precisely, orbits a common centre of gravity within a planetary system. That means size doesn't matter. A moon can be as massive as Ganymede, larger than Mercury, or as small as a rock a few hundred metres wide. As long as it's gravitationally bound to a planet and not to the sun, it qualifies. But even that criterion starts to falter at the edges. Binary systems like Pluto and Charon share a centre of mass that lies outside both bodies. They orbit each other, not one around the other. So which one is the planet and which one is the moon? Or are they both, depending on perspective? That same ambiguity extends across the solar system. Many moons around Jupiter, Saturn, Uranus, and Neptune are captured objects, asteroids or fragments that happen to fall into stable orbits. Some of them have such elongated paths that they stretch nearly to the limit of the planet's gravitational reach, where the pull of the sun begins to compete. At that point, can we still say they truly orbit the planet? Gravity doesn't draw clear borders. It fades gradually, and with it, our definitions fade too. There's also the question of permanence. Some moons are temporary, staying for only a short time before being ejected or pulled apart. Around Earth, small asteroids sometimes become temporary satellites, completing a few orbits before escaping back into space. For those brief moments, they meet every technical requirement of being a moon. They orbit Earth, they are gravitationally bound, and they are natural. Yet we rarely think of them that way. Their transience makes them feel less like companions and more like visitors. In contrast, some moons are almost permanent in their stability. The large ones, like Jupiter's Galilean moons, Saturn's Titan, or Neptune's Triton, have orbits that have remained unchanged for billions of years. They move with their planets like extensions of them, shaping their magnetic fields, influencing their atmospheres, and sometimes even contributing material to their rings. These moons aren't separate worlds so much as they are parts of larger systems, bound by shared origins. Another way to define a moon is by its formation. many formed from the same disk of material that built their parent planet. These irregular moons, aligned, circular, consistent. Others were born from collisions. Earth's moon likely formed that way, created when a Mars-sized body struck the early Earth and sent molten debris into orbit. That debris coalesced into a single sphere, cooling into the world we now know. Pluto's largest moon, Saturn, may have formed in a similar way from the remnants of a massive impact. And then there are the captured moons, objects that formed elsewhere, wandering through space until gravity caught them. Phobos and Deimos around Mars and Triton around Neptune are examples of this type. Their paths are tilted, irregular or retrograde, betraying their foreign origins. Each formation story gives us another layer of meaning for the word moon. Yet, as science continues to expand, even these categories blur. Some moons straddle boundaries between definitions. They might be captured objects but also contribute to rings, or they might form within a ring system and later drift outward. Others could have started as binary asteroids that became trapped together around a planet. These combinations defy neat classification. When nature forms something, it doesn't consult definitions, it just follows gravity. If we look deeper into the mechanics, the distinction between a planet and its moon becomes a question of dominance. Which body exerts more gravitational control? The dividing line is called the Hill sphere, the region around a planet where its gravity outweighs the sun's. Any object orbiting within that sphere is considered part of the planet's domain. But even that definition depends on distance, mass, and velocity. A small moon far from its planet might drift near the edge of that sphere, where the sun's influence begins to tug it away. Over millions of years, that tug could destabilize its orbit, pulling it free. If it escapes, it becomes a new kind of object. Not a moon anymore, not yet an asteroid. A wanderer between categories. This ambiguity makes moons some of the most conceptually fascinating objects in the solar system. They occupy the space between planets and asteroids, between permanence and transience, between birth and capture. They are intermediaries, records of interaction. Every moon is a story of how one body's gravity shaped another's fate, and because of that, their definitions are flexible. The solar system itself seems comfortable with uncertainty, as if it never intended its worlds to fit into simple labels. The debate about what qualifies as a moon mirrors the one about what qualifies as a planet. Both depend on context, on what we've seen, and what we expect. When astronomers redefined planet in 2006, they deliberately avoided addressing moons, perhaps because they understood how complex the issue could become. For now, the informal consensus is practical. If it orbits a planet rather than the sun, and if that orbit is stable and natural, we call it a moon. It's a definition that works well enough, even if it leaves room for exceptions. Still, within that simplicity lies depth. The word moon carries emotional weight because it connects motion to companionship. It implies relationship, one body moving around another, held not by choice but by gravity. It's a reminder that isolation in space is never complete. Every planet, even the smallest, seems to find something to circle it. Every world attracts, and every attraction leaves a trace. When we look at the solar system through that lens, moons become more than satellites. They are the visible expressions of connection. Earth's tides, Jupiter's volcanic heat, Saturn's rings, Neptune's backward companion, all of them exist because of moons. Their orbits redistribute energy, shape weather, and maintain balance. Without them, many planetary systems would be unstable or incomplete. In that sense, moons aren't just additions to planets, they're essential parts of their systems. Even the smallest fragments, the temporary captures, the ring-embedded moonlets, the co-orbital companions, contribute to the structure of their environments. Around Saturn, for example, tiny moons like Pan and Daphne sculpt the edges of the rings, maintaining order through gravitational resonance. Around Jupiter, small irregular moons interact with larger ones, creating subtle patterns in motion. Around Mars, Phobos's slow inward drift will eventually create a ring, transforming its relationship with the planet. Each example shows that moons aren't passive, they're active participants in shaping the solar system's architecture. And then there's the question of scale. Some moons, like Ganymede and Titan, are so large that they resemble planets more than satellites. They have atmospheres, weather, and possibly even oceans. If they orbited the Sun instead of their parent planets, we would likely classify them as planets themselves. The only difference is context, who they orbit, not what they are. That raises a quiet, fascinating idea. That identity in space is relative. A world's classification depends not on its composition or appearance, but on its relationship to something larger. That relativity is what makes the question so enduring. When does an object stop being a moon and start being something else? What if a large moon drifted away and began orbiting the Sun independently? Would it become a planet? And if a small planet were captured by a larger one, would it become a moon? These aren't just hypotheticals. They are possibilities that may have happened in the past or could happen again. The solar system is dynamic, and boundaries shift. What we call a moon today might not remain one tomorrow. Even the term double planet has entered discussion, describing systems like Pluto and Charon where both bodies are similar in size and orbit a shared point outside either world. Some scientists propose that Earth and the Moon could qualify as a double planet, since their shared centre of gravity lies relatively far from Earth's centre. Others reserve that label for more balanced pairs. The truth is, the line between planet and moon is more of a gradient than a boundary. It's another example of how definitions simplify what nature complicates. If you step back and think of the solar system as a single structure, moons reveal its texture. They are the fine details, the smaller orbits nested within larger ones. Without them, the planets would seem too smooth, too isolated. Moons give the system character. They show how gravity weaves connections across scales, how large bodies influence small ones, and how motion is shared. They are the punctuation marks in the solar system's long sentence, the pauses, the rhythms, the quiet companions that make the structure readable. In the end, perhaps a moon isn't defined by size or shape or permanence, but by relationship. It's something that exists in orbit, a state of balance between falling and flying. Every moon is a record of that balance. It's not simply a smaller body following a larger one, but a participant in a shared motion, both bound by and influencing the other. When we say moon, what we really mean is the visible trace of gravity's conversation, and that conversation is never still. As time continues, orbits shift, collisions happen, captures occur, and new moons are born. Some may dissolve into rings, others may coalesce into larger bodies. The solar system remains alive through motion, and its moons are the most graceful evidence of that motion. The question of what makes a moon will never have a final answer, because the system itself never stops changing. Even now, as we refine our definitions, new observations challenge them. Temporary captures blur the edges, binary systems redefine hierarchy, exomoons around distant stars expand the vocabulary. Each discovery asks us to reconsider what we thought was clear. The word moon persists not because it's precise, but because it's adaptable. It carries both scientific meaning and emotional resonance, linking physics with the language of connection. If you imagine the solar system without labels, without distinctions between planet, moon, or asteroid, what remains is motion. Everything circles something else. Everything is both center and satellite depending on perspective. The sun holds the planets hold their moons, and the moons hold echoes of smaller orbits within. The pattern repeats infinitely, fractal and harmonious. In that view, the idea of a moon becomes not a category, but a role, a temporary position in the endless choreography of gravity. And perhaps that's what defines a moon most accurately. It's not what it is, but what it does. It moves around something, and in doing so shapes both itself and its partner. That act of orbiting, of participating in shared motion, is universal. It's what links a dust grain in Saturn's rings to our own moon and to whatever satellites circle planets around distant stars. In the vast scale of space, every moon is both small and infinite, part of a pattern that repeats wherever gravity exists. Somewhere in that quiet realization lies the next question. Not how to define moons, but how to understand the relationships they represent. Because if every orbit is a form of companionship, then every moon, no matter how faint or small, is a trace of that companionship written into motion. The solar system's story, told through its moons, is a story of connection, constant, dynamic, and unfinished. And as we drift farther outward through this thought, the scientific question begins to soften into something quieter. If moons are companions to planets, then perhaps they also mirror something in us. The need to circle, to be connected, to share motion with another body, even across emptiness. When we look at the solar system, we often think of distance, vast spaces between worlds, light years of emptiness stretching from one point to another. But what we find instead, again and again, is companionship. Planets circle the sun. Moons circle planets. Even comets and asteroids sometimes travel in pairs. Gravity draws everything into relationship, turning isolation into orbit. It's one of the quietest truths of the universe, that motion connects what emptiness separates. Each moon, each pair of worlds carries that truth in its path. Earth and its moon share it visibly. Their relationship is slow and gravitational, but it's also ancient and influential. The moon's pull shapes the tides, balances Earth's rotation, and stabilizes its tilt. Without that companionship, our planet's climate would be unstable, our nights darker, our sense of rhythm different. The moon's presence has given structure to time itself, the month, the cycle, the light that divides darkness. Our first calendars were drawn from its phases. Our first stories were told under its reflection. Its orbit isn't just physical, it's woven into our culture and biology. That pattern repeats far beyond Earth. Around Jupiter, the Galilean moons orbit in precise resonance, their movements locked together by gravity's invisible rules. Io completes 4 orbits for every 2 of Europa's and 1 of Ganymede's. This resonance keeps their orbits slightly elliptical, creating internal friction that drives heat, volcanism, and, in Europa's case, liquid oceans. Without that gravitational companionship, without their constant tugging on one another, these worlds would be silent and frozen. Their relationship gives them energy. It keeps them alive in motion. Saturn's system shows the same pattern in a gentler form. Its moons shepherd rings, guide material, and maintain order in a place that could easily collapse into chaos. Pan and Daphnis carve gaps within the rings, their gravity shaping boundaries that ripple like waves. Titan exchanges material with the planet's magnetosphere. Enceladus feeds the faint E-ring with water vapor from its plumes. Each orbiting body contributes something to the larger harmony. Alone, they would drift and fade. Together, they create structure. Even in the farthest reaches, companionship persists. Pluto and Charon orbit one another, locked face to face, neither truly dominating the other. Their balance is so precise that the point of gravity lies between them, a visible symbol of equality. They turn together, side by side, in a dance that will continue for millions of years. In that stillness, they demonstrate that companionship doesn't always mean dependence. Sometimes it's symmetry. 2 bodies moving together because neither can escape the other's pull, nor wishes to. If you could look at all these pairs and systems at once, from the bright face of our moon to the shadowed ice of Triton, you would see that companionship is everywhere. Gravity ensures it. Every large body gathers smaller ones. Every motion creates resonance. Solitude in space is rare. Even when a planet seems alone, it's still connected by invisible forces to something else, to the sun, to the stars, to the passing pull of other worlds. The entire solar system is a network of relationships, a choreography of orbits where everything influences everything else. And that pattern feels familiar, not in a mystical way, but in a quiet, human one. We too exist in systems of companionship. We orbit families, communities, and memories. We move around each other in subtle gravitational ways, shaped by connection, by pull and release, by proximity and distance. Just as planets tug gently on their moons, we influence one another through presence. Sometimes the balance is stable, sometimes it shifts. Some connections last for billions of years in cosmic terms. Others are brief encounters that leave traces nonetheless. The physics of motion and the psychology of companionship share a structure. Both are built on the exchange of energy, the maintenance of balance, and the invisible strength of attraction. In every system we've studied, companionship changes the participants. Earth's rotation has slowed because of its moon. The same tidal forces that raise our seas also lengthen our days. Jupiter's moons shape one another's internal structures through their gravitational resonance. Saturn's rings would spread into diffuse dust without the tiny moons that herd them. In companionship, change is inevitable. Motion creates evolution. A body can't orbit without being altered by what it orbits. The same is true for us. Relationships shape who we are, just as moons shape the planets they circle. That's one of the reasons scientists study moons so closely. They are records of interaction. Their surfaces and orbits preserve evidence of how gravity, impact, and time reshape worlds. The craters on our moon are the memory of Earth's ancient bombardment. The fractures on Europa are the frozen signature of tides. The grooves on Ganymede mark the tension of internal motion. Each pattern tells a story of how companionship leaves a mark, subtle or deep, but always present. Even temporary relationships have influence. When a small asteroid is captured briefly by Earth or Jupiter, its path bends, its speed changes. The encounter alters both bodies, even if only slightly. No interaction is without consequence. In this sense, companionship in space is less about permanence than about exchange. It's about the transfer of momentum, energy, and history. The same is true for all forms of connection. Even when brief, they change trajectories. Some moons reflect light more than they produce it. Our moon doesn't shine, it glows with sunlight reflected from Earth's day. That reflection gives night its gentle brightness. It's an image of companionship, one body sharing the light it receives with another. The same happens around other planets. Saturn's moons illuminate its rings, Jupiter's reflect sunlight through its shadowed bands, even Pluto's faint moons scatter light across its surface, brightening regions that would otherwise be dark. In a system built on gravity, light also becomes a form of sharing. If you look at the solar system as a metaphor, every orbit becomes a story of relationship. Some are stable partnerships, like Pluto and Charon. Some are unequal but nurturing, like Earth and its moon. Some are turbulent, like Mars and its doomed moon Phobos, slowly spiraling inward. And some are so fleeting they leave barely a trace. Together they make a mosaic of companionships, different in form but united in principle. Each shows that motion is rarely solitary. Every world belongs to another's field of influence, just as every moment of life exists in relation to something else. The poetry of companionship isn't in the romance of space, it's in the structure of how things move. Gravity doesn't choose partners, it creates them through presence. Place any two masses near each other, and they begin to interact. Their mutual pull defines their relationship. They don't need communication or intention. The connection exists because they exist. That's the simplest form of togetherness. Existence shared through interaction. Over time, these connections evolve. Some moons drift farther from their planets, as Earth's moon does, moving a few centimeters away each year. Others spiral inward, like Phobos, destined to break apart and form a ring. The relationships between bodies shift as energy transfers between them. It's an exchange written in physics but resonant in meaning. Companionship at any scale requires adjustment. It isn't static. It changes as the participants change. Even the balance between planets and the Sun is a kind of companionship. The planets orbit because they fall endlessly toward the Sun but never reach it. It's a form of perpetual approach, attraction balanced by momentum. That same pattern repeats at smaller scales with moons and planets. Falling and flying coexist perfectly, each motion sustaining the other. It's stability built on tension, harmony built on difference. If you were to watch the solar system from a great distance, you wouldn't see stillness or emptiness. You'd see motion upon motion, large orbits nested within small ones, planets circling the Sun while moons trace loops around planets, each path slightly unique, yet synchronized by the same gravitational pulse. It's a vast choreography, silent and slow yet continuous. That motion is companionship made visible. It's what connects every body to another. Perhaps that's why so many of the ancient stories about the moon and stars were stories of relationship. People saw connection long before they understood gravity. They saw the moon follow the Earth, the planets move with regularity, the stars form patterns that never broke. They projected companionship into the sky because it was already there, not metaphorically but physically. The cosmos itself is relational. Every structure depends on something else. Even comets, often thought of as solitary travellers, are shaped by companionship. Their orbits are defined by planets that perturb their paths, by the sun that warms them, by the stars that tug subtly from afar. When a comet passes near a planet, its speed changes. When it passes near the Sun, it transforms, releasing gas and dust that form its tail. It never moves untouched. Its journey, like everything else in the solar system, is guided by unseen partnerships. In the outer darkness, companionship becomes even more delicate. A dwarf planet and its small moon, drifting far from light, share mutual warmth through gravity alone. Their orbit generates tiny amounts of heat, enough to keep internal layers stable. They move together through the cold, creating energy simply by existing in relation. Even there, at the farthest edge, companionship sustains motion. The same principle that governs moons also applies to galaxies and stars. Binary stars orbit one another, exchanging mass and light. Entire galaxies interact, merging over billions of years into new forms. The universe itself at every scale is structured by companionship. Nothing exists entirely alone. The spaces between things are filled with influence, gravitational, electromagnetic, or simply the potential for interaction. The poetry lies in the consistency of that pattern. If you think of the solar system as a kind of music, the moons are its harmonies. They echo the main themes played by the planets, adding texture and rhythm. Their orbits create resonance, their movements build chords of motion. Remove them, and the melody becomes thin. The system would still exist, but it would lose its balance and its complexity. Companionship makes the music fuller. To see this pattern clearly is to understand that connection is not an anomaly, it's the natural state of matter. From the smallest particles to the largest galaxies, everything moves in relation to something else. The solar system is just one visible instance of that rule. The companionship of moons and planets is a quiet reflection of a universal truth, that isolation is rare and relationship is the default shape of existence. And as we drift farther through thought, beyond numbers and definitions, that realization begins to soften into something almost personal. When we look at moons circling their planets, we aren't just seeing physics, we're seeing continuity, the way motion preserves connection across time. It's the same continuity that holds galaxies together, that binds atoms, that links our smallest actions to larger patterns. The companionship of celestial bodies is not symbolic of something deeper. It is the thing itself, the fundamental rhythm that underlies everything. Even when we can't see it, it persists. The moons hidden in shadow, the ones we haven't found yet, the faint bodies orbiting in darkness, all continue their paths, bound to their companions by invisible ties. They remind us that connection doesn't require light to exist. It continues quietly, beyond visibility, beyond awareness. Companionship, like gravity, is constant. And as the solar system continues its endless motion, these relationships endure. They shift, stretch, evolve, and sometimes end. But the pattern remains. The planets keep their moons, the moons keep their orbits, the sun keeps its hold. Each connection sustains another. It's a structure built not of solidity, but of motion, an architecture of companionship that defines what it means to belong to something larger than yourself. As the solar system drifts endlessly through the galaxy, every planet, moon, and piece of dust moves with it. Nothing stays still. The entire system, from the sun to the smallest fragment in the Kuiper Belt, orbits the galactic center once every 200 million years. It's a slow migration, an arc so vast that no living thing will ever witness its completion. And yet, through that immense motion, everything remains connected. Each orbit, each companion, each unseen moon continues its own smaller path, layered within that greater curve. The scale changes, but the principle remains the same. Everything moves around something else. We have followed that pattern outward, from the moon above our oceans to the moons of Jupiter and Saturn, to the hidden companions of the distant worlds. We've traced orbits through darkness, through silence, through distances too large to measure in anything but light and time. And as we begin to turn our thoughts inward again, returning from the edge of the solar system toward the world that first looked up and wondered, it becomes clear that the motion we've been describing isn't just astronomical, it's personal. It's a pattern reflected in everything we do. The moon above Earth has been moving slowly away from us for 4 billion years. Each year it drifts about 4 centimeters farther, its orbit widening as tidal interactions transfer energy between the two bodies. That movement is imperceptible day to day, but measurable over centuries. It changes the length of Earth's day, slowing our rotation fractionally. It changes the tides, subtly altering the rhythm of our oceans. Even as it recedes, the connection remains. The moon and Earth are locked in a long, quiet exchange of energy, a partnership built on gravity and time. That relationship is ancient and ongoing, a reminder that motion doesn't require closeness to remain meaningful. If you stand on a coastline at night and watch the moon reflected on the water, what you're really seeing is that connection made visible. The pull of the moon lifts the oceans toward it, creating tides that circle the planet. Those tides are the trace of gravity's conversation, energy moving between bodies across hundreds of thousands of kilometers. Every wave, every shifting current, every rhythm of rise and fall is shaped by that companionship. Even now, the same force that moves galaxies bends the surface of our seas. When humanity first looked up, that reflection was a mystery. The moon seemed perfect, unreachable, eternal. We drew patterns from its cycles, measured time by its phases, and imagined meaning in its light. It became part of our language, a symbol of longing, reflection, repetition. For most of human history, it was the nearest example of another world, a constant presence that moved but never left. When we finally reached it, we found it dry, silent, and marked by impact. A landscape carved by time and motion. But standing there, looking back at Earth, the pattern reversed. The planet that had once been the center of everything became the companion, blue and bright, suspended in darkness. From that distance, home looks small but connected, One more world in an endless family of worlds. That image, Earth seen from the moon, changed how we understand ourselves. It showed us that we're not separate from the universe, but part of it. Our world, with its oceans and air and cities and forests, is just another orbiting body, held in place by the same forces that move Jupiter's moons and Saturn's rings. The line between Earth and sky disappeared. Everything became one system, one continuous structure of motion. Back on Earth, the moon continues its steady path. It rises and sets, waxes and wanes, repeating patterns that have outlasted species and civilizations. It has no light of its own, yet it brightens our nights. It shapes our tides, our sleep, our imagination. It reminds us of what companionship means. Something constant yet changing, distant yet influential. When the night is clear and the air is still, you can feel the scale of that connection. It's not just visual, it's physical. Gravity doesn't require sight to act. The same invisible pull that binds the moon to Earth binds us to everything else. When scientists calculate orbits, they measure distances, velocities, and masses. But the numbers are only part of the story. What those equations describe is balance, the way attraction and motion counteract each other perfectly. Every moon, every planet, every asteroid follows that balance. If it moves too slowly, it falls inward. Too quickly, it escapes. The ideal orbit lies in between, where the two forces meet in harmony. That harmony is the quiet essence of companionship. Neither dominance nor distance, but equilibrium. If you trace that idea across the solar system, you see that balance everywhere. Jupiter's moons pull on one another just enough to maintain resonance without chaos. Saturn's ring moons hold the structure of the rings without breaking them. Pluto and Charon orbit a shared centre, equal in pull and motion. Even the Sun and its planets maintain a kind of mutual relationship. The Sun holds them with gravity, but they stabilise its rotation and maintain the distribution of angular momentum that defines the system's order. Nothing moves entirely alone. Every body modifies every other, subtly, continuously. That realization makes the solar system feel less like a collection of objects and more like a single organism. Each part depends on the others. Moons shape planets, planets shape stars, stars move within galaxies. The pattern repeats upward and downward through scale. From a distance, the system might appear still, but it's alive with motion, countless small relationships sustaining larger ones. The same logic applies everywhere. Connection creates stability. Returning to Earth after travelling outward in thought, the familiarity of home feels different. The same moon that lights the night now carries the weight of everything it represents. The prototype of every orbit, the symbol of every relationship that gravity sustains. When we talk about other moons, Io, Europa, Titan, Enceladus, Triton, we're really extending that original pattern outward. Each one is a variation on the same theme. Each one circles, reflects, and balances. Together, they form the physical poetry of connection, the universe's way of ensuring that no motion happens alone. The moon's effect on Earth is more than aesthetic. It stabilizes the planet's axial tilt, keeping our seasons consistent. Without it, the tilt would vary chaotically, leading to extreme climate shifts. Life as we know it might never have formed. Its presence has literally made the planet habitable. Its absence would change everything. That quiet dependency, invisible in daily life, is one of the deepest forms of companionship imaginable. It shows that even at planetary scales, survival depends on relationship. If you look beyond the moon, beyond Earth's atmosphere, beyond even the outer planets, that same pattern holds. The galaxies themselves are bound in clusters, orbiting one another through the slow pull of dark matter. Stars move in pairs or groups, their gravities lock together across light years. Binary systems exchange mass, energy, and light. Some stars even orbit black holes, moving in precise curved paths that mark the border between existence and oblivion. The universe never outgrows companionship, it just scales it upward. What's remarkable is that the same equation, Newton's law of universal gravitation, describes it all. The same rule that explains the moon's pull on our tides also governs the motion of galaxies. The difference is only in scale. The formula is simple: two masses, a distance between them, and a constant. From that, everything follows: orbits, tides, seasons, balance, and the quiet persistence of motion. The whole universe moves by the same logic of attraction and balance. The word orbit might sound mechanical, but its meaning is soft. It implies return, a path that bends but never ends. To orbit is to fall forever and never reach the ground. It's motion that repeats, always familiar, never identical. Every night when the moon crosses the sky, we witness that repetition. It's not static, it's ongoing. Each phase, each cycle, each rising and setting is slightly different from the last. That small imperfection keeps the system alive. We've often used the moon as a metaphor for reflection, but in a physical sense it truly is one. It reflects sunlight back to Earth, but it also reflects the shape of our own motion. When we watch it, we're seeing the curve of our orbit from a distance. The moon's path is Earth's mirror. It shows how we move through space without feeling it, how we're part of a rhythm too large to perceive directly. It's a reminder that even standing still, we are in motion, rotating, revolving, participating in an immense choreography that never pauses. As our understanding of the solar system deepens, that awareness grows. We know the moon formed from impact, that it's moving away, that its orbit affects everything from tides to days. But beyond the data, there's still the experience, the visible companionship of light and darkness. No matter how far we explore, that image remains the anchor. The first step outward from Earth began with looking up at that light. The last step home will always pass through it. If you imagine all the moons together, from Earth's single companion to Jupiter's crowd, from Saturn's ringed shepherds to Neptune's backward traveller, the system becomes a web of motion, an endless loop of attraction and response. Each moon, each planet, each orbit contributes to the same quiet structure. The entire solar system could be thought of as one extended relationship, built from countless smaller ones. The gravity that binds them all is the same force that binds galaxies and holds atoms together. It's the one true constant of companionship, the universal inclination toward connection, and yet, for all its vastness, that pattern brings us back to something small and human. The moon above our planet is both the simplest and most profound example of that rule. It circles silently, changes predictably, and lights the night without effort. It has been watching since long before we existed, and will continue long after we're gone. It asks nothing, gives everything, and never breaks its orbit. That quiet reliability is why it feels familiar, even comforting. It's the reassurance that some forms of companionship never fail. When astronauts stood on its surface and looked back, they saw Earth suspended in blackness, small, bright, fragile. That image, captured on film, became one of the most important in human history. It showed not separation but connection, not isolation, but relationship. The moon wasn't just another place. It was a perspective, a way of seeing our planet as part of a system rather than apart from it. That view still defines how we think about home. As we return in thought from the outer solar system to our own world, the journey closes not with finality but with continuity. The same motion that carries moons around planets carries us through our days. The same gravity that binds Jupiter's swarm holds our oceans to Earth. The same patterns of orbit and resonance that structure the solar system shape the balance of everything from weather to time. We live inside that motion, not apart from it. Every second, every rotation, every tide is part of the same rhythm, and when the night comes, that rhythm becomes visible again. The moon rises slowly, climbing through layers of air, casting pale light across water, rock, and cloud. It follows its path with silent precision, drawing arcs through time. It reminds us that movement doesn't end, that cycles continue whether we notice or not. The moon is both a clock and a mirror, marking the passage of time and showing us where we stand within it. A final orbit home doesn't mean arrival or completion. It means awareness, the recognition that home is part of the same pattern we've been tracing. The solar system isn't something outside us. It's something we live within. Its gravity holds us. Its motion carries us. Its companionship defines us. To return home from a journey through space is to understand that we never left it. We have always been orbiting, always been part of the same shared motion that links the moon to Earth, Earth to the sun, and the sun to the stars beyond. In that realization, the search ends quietly. Not because everything is known, but because everything connects. The count of moons becomes less important than the rhythm they follow. The numbers fade, the motion remains. The solar system continues, its countless companions tracing paths through time, their light and shadow marking the infinite conversation between bodies that will never stop moving. And here, beneath that sky, under the same reflected glow that has guided us since the beginning, we continue our own orbit, small, steady, and shared with everything that moves through this same expanse of night.